There is something wrong with the universe. Not wrong in the way a machine breaks down, not wrong in the way a calculation produces an unexpected remainder. Wrong in a way that cuts much deeper than that. Wrong in a way that reaches into the foundations of everything you have ever been told about reality, and quietly, methodically begins to pull those foundations apart. You have been living inside a story about how the universe works. That story was built by some of the most brilliant minds in human history. It was tested, refined, confirmed, and celebrated. It was supposed to be complete, or at least nearly complete. And then the instruments got better. The observations got sharper. The measurements became more precise. And something started showing up in the data that was never supposed to be there. Something that does not fit. Something that should not exist. And the more carefully scientists look at it, the worse it gets. You need to understand what that means, because it is not a small thing. It is not a footnote in a journal that will be quietly corrected in the next edition. It is not a rounding error that will disappear once someone rechecks the math. What is being discovered, piece by piece, observation by observation, is that the universe, the actual, physical, real universe in which you exist, in which every atom of your body is embedded, is behaving in ways that our best models of reality cannot fully account for. And the gap between what our models predict and what is actually happening is not closing, it is growing. The more we measure, the more the universe seems to be telling us that something about our deepest understanding of it is not just incomplete. It may be fundamentally, structurally wrong. Think about what that sentence means. Fundamentally wrong. Not the kind of wrong where you add a few more variables to the equation and everything resolves itself. Not the kind of wrong where a new telescope provides better data and the anomalies disappear. The kind of wrong where the entire framework, the conceptual architecture upon which modern physics is built, may need to be dismantled and rebuilt from the ground up. That is the conversation happening right now in hushed and not so hushed tones among physicists, cosmologists, and mathematicians who have dedicated their entire lives to understanding reality. They are starting to admit, some openly, some reluctantly, that the universe is not working the way it should. And they have the data to prove it. This is not a story about alien conspiracies or pseudoscience or fringe theorists operating outside the boundaries of legitimate inquiry. Every single piece of evidence we are going to walk through together comes from peer-reviewed research, from Nobel Prize-winning experiments, from instruments built at enormous cost and operated by teams of hundreds of scientists over decades. The strangeness we are going to explore is not the product of speculation. It is the product of rigorous, careful, honest science. And that is precisely what makes it so unsettling. Because when you can no longer dismiss the anomalies as noise, when the best minds on the planet confirm them independently using different methods and different instruments and different theoretical approaches, and they all point to the same disquieting conclusion. You are no longer dealing with a mystery you can comfortably set aside. You are dealing with a fundamental problem with reality itself. So before we go any further, before we start dismantling the picture you have always had of the cosmos, let us start at the beginning. Let us revisit what we thought we knew. Because the only way to truly feel the weight of what is wrong is to first understand how magnificent, how airtight, how deeply satisfying the standard picture of the universe once felt. The story of modern physics is one of the greatest intellectual achievements in the history of our species. It deserves to be told, with the reverence it is due, even as we prepare to watch parts of it begin to crack. For most of human history, the universe was a mystery that lived entirely in the domain of myth and philosophy. The stars were gods, or the eyes of gods, or the fires of heaven. The motion of the planets was divine choreography. The earth was the center of all things, and all things revolved around it in perfect circles, because perfection was what the divine demanded. Then, slowly, painfully, over the course of centuries, that picture began to change. Copernicus dared to suggest that the earth moved. Galileo pointed a crude telescope at Jupiter, and watched its moons trace orbits around a body that was not the Earth. And the old story began to fracture. Newton sat beneath his apple tree, or perhaps not literally, but the myth captures something true about the moment, and he perceived a connection between the falling of a small fruit and the motion of the moon. And in that perception he glimpsed something extraordinary. The universe runs on rules. Consistent, mathematical, universal rules that do not care whether you are an apple or a planet, whether you are on Earth or somewhere in the incomprehensible depths of space. Newton's laws of motion and his law of universal gravitation were breathtaking in their power. You could write down a few equations, plug in the positions and masses of astronomical bodies, and predict with stunning precision where those bodies would be years, decades, centuries into the future. When the planet Uranus was discovered in 1781, astronomers noticed that its orbit had small irregularities. It was not moving quite the way Newton's equations predicted it should. Rather than abandoning the equations, they trusted them. They reasoned that there must be another undiscovered planet whose gravitational influence was disturbing Uranus's path. They calculated where that planet should be. They pointed their telescopes at the predicted location, and there it was. Neptune, discovered not by sight first, but by mathematics first. The universe had been asked a question in the language of equations, and it had answered correctly. That moment, the discovery of Neptune through pure mathematical prediction, established something profound in the human relationship with science. It established trust, the kind of trust that is earned through demonstration, through verifiable, repeatable proof. It said, if you understand the rules deeply enough, you can know things about reality before you have even looked at it. You can predict the universe, you can anticipate it. The cosmos, in all its vastness, is not a chaos. It is a lawful system, and those laws are discoverable, and once discovered, they give you power over nature that nothing else in human experience has ever provided. This was not just a scientific revolution, it was a philosophical one. The universe had revealed itself to be, at least in principle, fully comprehensible. Then came the 19th century, and James Clerk Maxwell sat down with a set of equations describing electricity and magnetism, and he discovered something almost accidental in its elegance. When he combined his equations in a particular way, they predicted the existence of waves that propagate through space at a specific speed. When he calculated that speed, it matched, almost perfectly, the measured speed of light. Maxwell had discovered, without intending to, that light is an electromagnetic wave. He had unified three apparently separate phenomena, electricity, magnetism, and light, into a single coherent framework. And the universe had answered again. It had confirmed, through independent measurement, what the equations had whispered. Light, the most intimate thing in human experience, the phenomenon that allows you to see the world, to see these words, turned out to be a ripple in invisible fields that permeate all of space. And then Albert Einstein arrived. Einstein, who was perhaps the most revolutionary intellect science has ever produced, did what very few minds in history have managed to do. He questioned the assumptions that lay so deep in our understanding of reality that no one else had even recognized them as assumptions. Newton's universe ran on a backdrop of absolute space and absolute time. Space was the stage on which events unfolded, and time was the clock that measured their unfolding, and both the stage and the clock existed independent of anything happening on them. Einstein looked at Maxwell's equations, noticed that they implied a fixed speed of light that did not change depending on the motion of the observer, and followed that implication to its logical conclusion. A conclusion so radical that it still, over a century later, requires a deliberate effort to absorb. Space and time are not absolute. They are relative. They bend, stretch, contract, and dilate depending on the motion of the observer and the strength of the gravitational field in which the observer finds themselves. The special theory of relativity, published in 1905, told you that time moves more slowly for a person traveling at high speed than for a person standing still. Not as a metaphor, not as a psychological illusion. Literally, physically, more slowly. A clock on a fast-moving spacecraft ticks more slowly than an identical clock sitting on the ground. This has been confirmed experimentally with atomic clocks on airplanes, with the global positioning. System satellites that allow your phone to navigate city streets, which must account for relativistic time dilation in order to function accurately. The universe bends time. That is not poetry, that is engineering fact. And then, in 1915, Einstein went further. He published his general theory of relativity, which reinterpreted gravity not as a force acting at a distance, as Newton had described it, but as a curvature of space-time itself, caused by the presence of mass and energy. Objects do not fall toward the Earth because the Earth is pulling them. Objects fall toward the Earth because the Earth's mass curves the fabric of space-time around it, and falling objects are simply following the straightest possible path through that curved geometry. What feels like a force pulling you down is the universe's geometry doing its work. The elegance of this picture is almost incomprehensible in its beauty. Space and time are not separate things. They are woven together into a single, four-dimensional fabric called space-time. Matter and energy tell that fabric how to curve. The curvature of the fabric tells matter and energy how to move. Everything in the universe, every planet, every star, every galaxy, every photon of light, is a participant in this continuous dynamic conversation between geometry and energy. And the equations that describe this conversation, Einstein's field equations, are among the most celebrated and verified in all of science. They predicted the bending of light around massive objects, confirmed during the solar eclipse of 1919. They predicted gravitational time dilation, confirmed by atomic clocks. They predicted the existence of black holes, objects so massive that not even light can escape their curved geometry. They predicted gravitational waves, ripples in the fabric of space-time itself, spreading outward from violent cosmic events. And in 2015, a century after the theory was published, the LIGO collaboration detected those waves, for the first time, produced by two black holes merging over 1 billion light-years away. The universe had spoken again in a new language, and Einstein's equations had translated it perfectly. Simultaneously with Einstein's revolutionary reimagining of the large-scale structure of reality, a different and equally radical revolution was occurring in the physics of the very small. Quantum mechanics, developed in the first 3 decades of the 20th century by a constellation of brilliant minds, Planck, Bohr, Heisenberg, Schrödinger, Dirac, Born, Pauli, and others, dismantled the classical picture of matter and energy in ways that are still, to this day, not fully integrated into our intuitive understanding of the world. At the quantum scale, the scale of atoms and their constituents, the universe does not behave the way it does at the scale of planets and baseballs. At the quantum scale, the universe is fundamentally probabilistic. You cannot know, even in principle, both the exact position and exact momentum of a particle simultaneously. This is not a limitation of your instruments. It is a feature of reality itself. Heisenberg's uncertainty principle is not a statement about measurement difficulties. It is a statement about what exists. A particle does not have a definite position and a definite momentum at the same time. Those are not things it possesses. They are things that emerge from the act of measurement. Before you measure a quantum particle, it exists in what is called a superposition, a kind of smeared-out, probabilistic cloud of all the different states it could be in. When you perform a measurement, the superposition collapses into a single definite state. But the act of collapse, the mechanism by which the universe goes from a range of possibilities to a single actuality, is not explained by the equations of quantum mechanics. It is simply inserted as a postulate, a rule, without any underlying physical account of how or why it happens. This is called the measurement problem, and it is one of the deepest unsolved questions in all of physics. But the theory built on top of this postulate, quantum mechanics and its successor, quantum field theory, makes the most precise predictions in the history of science. The anomalous magnetic moment of the electron, for example, has been calculated from quantum electrodynamics to 11 decimal places of precision. The experimental measurement agrees with the theoretical prediction to 11 decimal places. 11 decimal places. This is not coincidence. This is a theory that is right about something very deep. So here is where you stood, somewhere around the middle of the 20th century, surveying the landscape of physics. You had two towering, extraordinarily precise, experimentally verified theories. General relativity described the universe at the largest scales: planets, stars, galaxies, black holes, the entire cosmos, with breathtaking accuracy. Quantum mechanics described the universe at the smallest scales: atoms, electrons, photons, the fundamental building blocks of matter, with equally breathtaking accuracy. Together, they covered the full spectrum of known phenomena. They were not perfect, both had known limitations, and they were famously incompatible with each other in certain extreme situations, like the interior of a black hole or the beginning of the universe, where the very small and the very massive coexist. But that incompatibility seemed like a solvable problem, a gap that future theoretical progress would close. The overall picture was one of convergence. Physics was moving toward a final theory, a theory of everything that would unify gravity and quantum mechanics into a single, seamless framework. The universe was lawful, mathematical, and, in principle at least, fully comprehensible. You just needed to finish the job. And then the measurements got better, and the universe stopped cooperating. Let us begin with something that sounds like a technical disagreement between astronomers, but is, in fact, one of the most alarming things happening in modern science. It is called the Hubble tension, and to understand why it matters, you first need to understand what the Hubble constant is and why physicists care about it so intensely. The universe is expanding. You probably already know that. Edwin Hubble confirmed it observationally in 1929, and it has been one of the foundational facts of cosmology ever since. Galaxies are moving away from each other, carried apart by the expansion of space itself, not flying through space like fragments from an explosion, but riding the stretching of the fabric of space-time, the way dots drawn on the surface of a balloon move apart as the balloon is inflated. The rate at which this expansion is occurring is described by a single number, the Hubble constant, denoted h0, which tells you how fast the universe is expanding right now. Measuring the Hubble constant precisely is one of the central goals of observational cosmology. It is not just a number, it encodes the age, the size, the history, and the fate of the entire universe. If you know how fast the universe is expanding today, and you know the laws that govern that expansion, you can run the movie of cosmic history forward and backward. You can calculate when the Big Bang occurred, how old the universe is, how the large-scale structure of galaxies and cosmic filaments formed, and what will ultimately happen to everything that exists. The Hubble constant is, in a very real sense, one of the most important numbers in all of science. Now, there are two fundamentally different ways to measure it. The first way is called the distance ladder method, and it works by building up a sequence of overlapping measurement techniques that extend progressively outward through the cosmos. You start close, measuring distances to nearby stars using parallax, the tiny apparent shift in a star's position as Earth moves around the Sun, the same effect that allows you to perceive depth with two eyes. From those nearby stars, you calibrate a class of variable stars called Cepheids, whose brightness pulsates at a rate that is precisely related to their intrinsic luminosity. Once you know a Cepheid's intrinsic brightness, you can determine how far away it is by comparing that intrinsic brightness to how bright it appears in your telescope. Cepheids extend your reach to other galaxies. From those galaxies, you can calibrate type Ia supernovae, enormous stellar explosions that occur at a highly consistent intrinsic brightness, like cosmic lighthouses. Type Ia supernovae can be seen across billions of light years. By measuring the apparent brightness of these supernovae and comparing it to their known intrinsic brightness, you can determine the distances to extremely remote galaxies. And then, by measuring those galaxies' recession velocities, you can calculate the expansion rate of the universe. This is the distance ladder, a chain of overlapping methods, each calibrated by the one below it, extending from our cosmic neighborhood out to the farthest reaches of the observable universe. Teams using the distance ladder method, most prominently the team led by Nobel laureate Adam Rees using the Hubble Space Telescope, have arrived at a value for the Hubble constant of approximately 73 kilometers per second per megaparsec. This means that for every megaparsec, roughly 326 million light-years, of distance between 2 points in the universe, those points are moving apart at 73 kilometers per second due to the expansion of space. That value, 73, is extremely well measured. It has been confirmed by multiple independent teams using multiple independent implementations of the distance ladder approach. The error bars have been shrinking year after year as the measurements become more precise, and the value has remained stubbornly, robustly, consistently at around 73. But there is a second way to measure the Hubble constant, and it is completely independent of the first. Instead of looking outward through the present universe, you look backward to the very beginning, specifically to the cosmic microwave background radiation, the afterglow of the Big Bang itself. When the universe was very young, in its first few 100,000 years, it was a hot, dense, opaque plasma, a soup of protons and electrons so energetic that photons of light could not travel through it without being immediately scattered. Then, when the universe had expanded and cooled enough, electrons and protons combined to form neutral hydrogen atoms, and suddenly the universe became transparent. The photons that had been trapped in that plasma were released, flooding the cosmos with light. That ancient light, stretched by billions of years of cosmic expansion into the microwave range of the electromagnetic spectrum, is what we call the cosmic microwave background, or CMB. It is the oldest light in the universe. It fills all of space in every direction, and it carries, encoded in the subtle patterns of its temperature fluctuations, variations of less than 1 part in 100,000, an extraordinarily detailed record of the early universe. By studying these CMB fluctuations with incredible precision, using satellites like WMAP and the Planck Space Observatory, cosmologists can extract a detailed portrait of the early universe and, from that portrait, derive a prediction for what the Hubble constant should be today, based on the standard model of cosmology. This prediction is made not by measuring the expansion directly, but by modeling the physics of the early universe and calculating what value of the Hubble constant would produce the CMB pattern we actually observe. The Planck collaboration, after painstaking analysis of their satellite data, arrived at a Hubble constant of approximately 67.4 kilometers per second per megaparsec. That is their number 67.4. Very precisely measured, very confidently stated, based on the most detailed map of the early universe ever produced. And there you have it, 2 methods, both rigorously executed, both precisely measured. One gives you 73, the other gives you 67.4. The difference between them is roughly 5 to 10%, depending on exactly which measurements you compare. That might not sound large, but in the world of precision cosmology, this is an enormous discrepancy. The error bars on both measurements are small enough that the two values cannot overlap. They are statistically incompatible with each other at a significance level of roughly 5 sigma, which in the language of statistics means the probability that this disagreement is due to pure chance is less than 1 in a million. This is not a small tension that might dissolve when the uncertainties are properly accounted for. This is a genuine, deep, robust contradiction in our best understanding of the cosmos. You have to sit with that for a moment and feel what it actually means. The universe has a single expansion rate right now. That expansion rate is what it is. One number, not two. There cannot be 2 correct answers to this question any more than there can be 2 correct answers to the question of how old you are. And yet the 2 most powerful methods we have for measuring that number give results that are incompatible. If both measurements are correct, and multiple independent teams using different instruments and different techniques have confirmed both, then there is something wrong. Something wrong with our understanding of the history of the universe, Something wrong with our model of how it evolved from the hot, dense aftermath of the Big Bang to the structured, expanding cosmos we inhabit today. Something is missing from the story. Something important. Something that changes the numbers. Some researchers have looked carefully for systematic errors in one method or the other. A flaw in the calibration of the Cepheid distances, perhaps, or an unrecognized bias in the CMB analysis. These are legitimate things to check. Science is supposed to be self-critical, and indeed these checks have been performed obsessively, repeatedly, by teams on both sides of the tension and by independent groups with no stake in the outcome. The answer keeps coming back the same. The systematic errors are not large enough to explain the discrepancy. This is not a measurement error. This is a signal. The universe is telling us something, and what it is telling us may require a fundamental revision of our standard cosmological model, a model that has been the cornerstone of our understanding of cosmic history for decades. Some of the proposed explanations involve modifying the physics of the early universe in ways that are not currently part of our standard model. Perhaps there was an additional source of energy in the universe's early moments, something cosmologists call early dark energy, that affected the expansion rate before recombination and thus altered the CMB prediction. Perhaps there are additional light particles, beyond the 3 known types of neutrinos, that contributed to the energy density of the early universe in ways that shift the calculated value of the Hubble constant. Perhaps gravity behaves slightly differently on cosmological scales than Einstein's equations predict, in ways subtle enough to have escaped detection so far, but significant enough to account for the discrepancy in the expansion rate. None of these proposed solutions is satisfying in the way a real solution should be. Each one introduces new elements or modifications to the theory that themselves require justification. Each one solves the Hubble tension by introducing new puzzles of its own. But here is what is most important for you to carry forward as we continue. The Hubble tension is not the only crack in the edifice of modern cosmology. It is not an isolated glitch in an otherwise smoothly running system. It is one entry in a growing list of anomalies, a list that has been getting longer, not shorter, as our instruments improve and our observations become more precise. The universe, it turns out, has been accumulating discrepancies, and each one examined in isolation might be dismissed as a local problem awaiting a local solution. But when you step back and look at them together, a different and far more unsettling possibility begins to take shape. Let us talk about the 95%. Because here is something that the standard story of the universe almost never emphasizes with the weight it deserves. Approximately 95% of the universe, by total energy content, is completely unknown. Not unknown in the sense that scientists are currently studying it and expect to characterize it soon. Unknown in the sense that we have no confirmed physical theory of what it is, no laboratory detection of it, no direct observation of it. We know it is there because of what it does, because of its gravitational effects on the matter and light we can actually observe. But what it fundamentally is, at the level of particles and fields and underlying physical laws, remains entirely mysterious. 95% of everything that exists, the vast majority of the cosmos, is made of stuff we cannot identify, cannot detect directly, and cannot explain from first principles. The universe we can see, touch, probe, measure, and understand is approximately 5% of everything that exists. The 85% of that 95%, the largest single component of the mysterious, is called dark matter. And dark matter's story begins, as so many strange stories in science do, with an astronomer noticing that something does not add up. In the 1930s, a Swiss astronomer named Fritz Zwicky was studying the Coma cluster, a dense cluster of galaxies located about 320 million light-years from Earth. Zwicky measured the velocities at which individual galaxies within the cluster were moving relative to each other. He also measured the total mass of visible matter in the cluster, all the stars and gas that could be observed. And then he performed a straightforward calculation. Given the total mass of visible matter, and given the gravitational forces that mass could exert, Were the observed galaxy velocities consistent with what they should be? The answer was no. The galaxies were moving far too fast. If the only gravity acting on them came from visible matter, they should have been flying apart. The cluster should have been dissolving, but it was not dissolving. It was a stable, bound system. Zwicky concluded that there must be additional mass in the cluster that was not visible, mass that was providing extra gravitational glue, holding the cluster together. He called it dark matter, and he was largely ignored. Decades later, in the 1970s, astronomer Vera Rubin was measuring something different: the rotation curves of individual galaxies. A galaxy is a disk of stars, gas, and dust rotating around a central concentration of mass. If you think about how rotation works under Newton's laws of gravity, you expect the velocity of stars to decrease as you move farther from the center of the galaxy, just as the outer planets of the solar system orbit the sun more slowly than the inner ones, because the gravitational influence of the sun's mass diminishes with distance. Rubin painstakingly measured the rotation velocities of stars at various distances from the centers of multiple galaxies. And what she found was something that should not have been possible. The rotation curves were flat. The stars at the outer edges of galaxies were orbiting just as fast as the stars near the center, often even slightly faster. And this pattern persisted far out into the galaxy's periphery, well beyond the visible disk of stars and gas. The velocity curves simply refused to drop off as Newton's laws predicted they should. The implications of flat rotation curves are stark and inescapable. They mean there must be more mass in these galaxies than can be accounted for by the stars and gas we can see. And not just a little more mass, but a lot more. The additional invisible mass appears to extend outward in a large, diffuse halo surrounding the visible disk of the galaxy, contributing enough gravitational influence to keep the outer stars orbiting at the same speed as the inner ones. When you add up all the mass required to explain the flat rotation curves, galaxies are typically 5 to 10 times more massive than their visible components would suggest. The universe is fundamentally different from what it appears to be when you look at it with your eyes or your telescopes. The luminous matter, the stars, the gas, the visible stuff, is like the thin foam on the surface of a vast dark ocean. The real mass of the universe is invisible. Since Rubin's work, the evidence for dark matter has only grown stronger and more diverse. One of the most striking confirmations came from an event called the Bullet Cluster, two galaxy clusters that collided with each other billions of years ago, and whose separated remnant we can observe today. When galaxy clusters collide, the hot gas that makes up most of the visible matter slows down due to electromagnetic interactions and piles up near the collision point. But gravitational lensing, the bending of background light by the mass of the clusters, one of Einstein's predictions, tells us where the mass of the clusters actually is. And it is not where the hot gas is. The mass, revealed by gravitational lensing, is located ahead of the gas in two separate lobes, as if it passed through the collision without interacting. This is exactly what you would expect if most of the mass of each cluster is made of something that does not interact electromagnetically, something that can pass through another body of matter as if it were not there, unaffected, ghost-like. Dark matter. The cosmic microwave background, which we discussed earlier, also bears the imprint of dark matter. The precise pattern of temperature fluctuations in the CMB, the exact heights and positions of the acoustic peaks in what cosmologists call the power spectrum, is sensitive to the composition of the early universe. When you fit the standard cosmological model to the CMB data, you get a universe that is approximately 5% ordinary matter, 27% dark matter, and 68% dark energy. The dark matter component is required to reproduce the observed structure of the CMB. Without it, the peaks shift, the amplitudes change, the whole pattern becomes inconsistent with what Planck and other satellites have measured. Dark matter is not just needed to explain galaxy rotation curves or cluster dynamics. It is built into the fabric of the CMB, into the structure of the early universe itself, millions of years before the first galaxies ever formed. And yet, With all of this evidence demanding that dark matter exists, we have never detected a single dark matter particle directly. For decades, physicists have been building increasingly sensitive detectors, buried deep underground to shield them from cosmic ray interference, designed to catch the faint whisper of a dark matter particle passing through a tank of supercooled liquid xenon or germanium. The leading theoretical candidates, particles called WIMPs, weakly interacting massive particles, are predicted to occasionally bump into ordinary matter via the weak nuclear force, leaving a tiny, detectable signal. The detectors have gotten better and better. The sensitivity has improved by orders of magnitude. The expected signal has not appeared. The most sensitive dark matter detectors ever built have searched and found nothing. Every WIMP detection candidate has turned out to be background noise. The particle that was supposed to reveal itself when we looked carefully enough has remained stubbornly, perfectly invisible. This is a deeply strange situation. You have overwhelming gravitational evidence for a component of the universe that outweighs all visible matter by a factor of 5. You have that evidence confirmed by multiple independent observations across a huge range of scales, from individual galaxies to galaxy clusters to the entire observable cosmos. And you have not found the particle responsible for it anywhere, despite decades of dedicated searching with instruments of breathtaking sensitivity. Either dark matter is real, but made of something so exotic and weakly interacting that even our best detectors cannot find it, which simply means we need to look harder. Or something else is going on. Maybe dark matter is not a particle at all. Maybe it is something more exotic. Primordial black holes, sterile neutrinos, axions, or something entirely beyond the current catalog of theoretical possibilities. Or, and this is the possibility that some physicists are beginning to take more seriously, even though it requires modifying the most successful gravitational theory ever created, maybe our understanding of gravity itself breaks down in the low acceleration regime relevant to the outskirts of galaxies, and the anomalous rotation curves are not telling us about invisible matter, but about a failure of our gravitational laws. This alternative, called modified Newtonian dynamics or MOND, proposed by physicist Mordechai Milgram in the early 1980s, makes a specific prediction. When gravitational acceleration falls below a certain tiny threshold, the effective gravitational force on an object is stronger than Newton's laws predict. The beautiful thing about MOND is that it successfully predicts the rotation curves of a very wide range of galaxy types, using a single modification, a single adjustable parameter, without invoking dark matter at all. It also predicts a relationship called the radial acceleration relation, which describes a tight correlation between the observed gravitational acceleration in galaxies and the gravitational acceleration that would be predicted from visible matter alone. That correlation holds across an enormous range of galaxy types, from small dwarf galaxies to large elliptical ones, with very little scatter. It is exactly the kind of tight correlation you would expect from a modification to the law of gravity, and it is harder to explain within the dark matter framework, where the amount and distribution of dark matter in any given galaxy is not directly constrained by the visible matter. But MOND has its own severe problems. It cannot explain the bullet cluster. It does not reproduce the CMB power spectrum without effectively reintroducing something that behaves like dark matter. In its original form, it is not relativistic, and relativistic extensions of MOND are complicated and not universally accepted. The scientific community has not abandoned the dark matter paradigm in favor of modified gravity, and there are good reasons for that. But neither has it converged on a specific dark matter candidate or a confirmed detection. The debate continues, unresolved, at the frontier of theoretical and observational physics. And the fact that it continues, the fact that, decades after the dark matter problem was clearly defined, we still do not know what it is, should give you pause. This is not a small, easily solved puzzle. It is a fundamental gap in our understanding of what the universe is made of. Now let us turn to the dark energy problem, which is in some ways even more disturbing than dark matter. because it does not just ask us to add something new to our inventory of the universe's contents. It confronts us with a quantity that our best theory predicts so badly that the discrepancy is perhaps the single largest error in the history of quantitative science. In 1998, two independent teams of astronomers, the Supernova Cosmology Project and the High-Z Supernova Search Team, were measuring the distances to Type Ia supernovae in distant galaxies in order to map the expansion history of the universe. The expectation, shared by almost everyone in the field at the time, was that the expansion of the universe should be slowing down. The Big Bang had sent everything flying apart at enormous speed, and gravity, the mutual gravitational attraction of all the matter in the universe, should be acting as a brake, gradually decelerating that expansion. The question was not whether the expansion was decelerating, but how quickly. What the supernova teams found was the opposite. The distant supernovae were dimmer than expected, much dimmer. Not dimmer because they were intrinsically less bright, but dimmer because they were farther away than they should have been, given the expected deceleration of cosmic expansion. The universe was not decelerating. It was accelerating. The expansion of space was speeding up, not slowing down. Something was pushing the universe apart, overcoming the attractive pull of gravity and driving the galaxies apart at an ever-increasing rate. This discovery, which won the 2011 Nobel Prize in Physics for its leaders, Saul Perlmutter, Brian Schmidt, and Adam Rees, fundamentally changed our picture of the cosmos. The unknown force or energy field responsible for the acceleration was named dark energy. Dark energy, in the standard cosmological model, is represented by a single quantity called the cosmological constant, denoted by the Greek letter lambda. The same lambda that Einstein had introduced into his field equations in 1917, and then famously called his greatest blunder when Hubble's observations showed the universe was expanding. Einstein had added the cosmological constant to prevent his equations from predicting a dynamic, evolving universe, which they naturally did, because he believed the universe was static and eternal. When expansion was confirmed, he removed it. But the 1998 supernova discoveries brought it back, in a new incarnation, as the energy of the vacuum itself. Empty space, it turns out, is not empty. It has energy. And that energy, ARO 2.04, 2226, ARO 9, 1032. Continue, ARO 2.04.26, ARO 9, 1036. The energy of the vacuum itself acts as a kind of anti-gravity, a repulsive pressure that permeates all of space and drives the accelerating expansion we observe. The cosmological constant, in quantum field theory, has a natural interpretation. Quantum mechanics tells us that empty space is not truly empty. It is a seething, roiling foam of virtual particles, pairs of matter and antimatter that pop in and out of existence for vanishingly brief moments, borrowing energy from the vacuum and returning it before the universe has time to notice. These quantum fluctuations contribute energy to the vacuum, and that vacuum energy is the natural candidate for the cosmological constant. When quantum field theorists calculate the expected energy density of the vacuum from first principles, adding up all the contributions from all the known quantum fields, they arrive at a number, a specific, calculable prediction for how large the cosmological constant should be. And when you compare that theoretical prediction to the observed value of the cosmological constant, as measured from the accelerating expansion of the universe, you find a discrepancy that is so enormous, it is almost impossible to convey in ordinary language. The theoretical prediction exceeds the observed value by a factor of approximately 10 to the power of 120. That is a 1 followed by 120 zeros. In all of physics, in all of science, in all of human intellectual history, there has never been a theoretical prediction that was this wrong, not even close. The standard tools of quantum field theory, applied to the simplest and most natural estimate of vacuum energy, give an answer that is so catastrophically, absurdly larger than what we observe that the discrepancy cannot be a rounding error or a small overlooked factor. Something is canceling almost all of the vacuum energy, reducing it from the enormous value that quantum field theory predicts to the tiny value we actually observe. with a precision of 120 decimal places. That level of cancellation, if it is the result of some underlying mechanism, requires that mechanism to be tuned to 1 part in 10 to the 120th. That is fine-tuning of an almost unfathomable degree. This is known as the cosmological constant problem, and it has been described by physicists as the worst problem in theoretical physics, the most embarrassing failure of any theoretical framework to agree with observation. It is not a small error in a peripheral calculation. It is a catastrophic failure of our best physical theories when applied to one of the most fundamental questions about the universe. Why is the energy of empty space the value that it is? The problem was recognized in the late 1980s and has been a central puzzle of theoretical physics ever since. Enormous effort has been devoted to it. The proposed solutions fill entire textbooks, and none of them are satisfying. None of them have achieved consensus. None of them have been confirmed by experiment or observation. One of the most discussed proposed solutions is called the anthropic principle, which has a long and somewhat uncomfortable history in physics. In the context of the cosmological constant, the anthropic argument goes roughly like this. There may be an enormous number of universes, a multiverse, each with a different value of the cosmological constant, distributed randomly across a vast landscape of possibilities. In most of those universes, the cosmological constant is so large and positive that the universe expands so rapidly that matter never has time to clump together into galaxies, stars, and planets. Life cannot form. No one is there to observe anything. But in a small subset of universes, the cosmological constant happens, by chance, to be small enough that structures can form, stars can ignite, planets can coalesce, and beings can evolve who look up at the sky and wonder about the nature of reality. We find ourselves in one of those rare, structure-permitting universes simply because we could not exist in any other kind. The cosmological constant is small, not because of any deep, physical mechanism, but because small is the only value consistent with our existence. This argument, championed by physicists like Steven Weinberg, who made a quantitative prediction of the maximum allowed value of the cosmological constant on anthropic grounds before the 1998 supernova results, and whose prediction was remarkably close to the value eventually measured, is intellectually serious. It is not the domain of crackpots, but it is deeply uncomfortable for many physicists because it is not in the traditional sense an explanation. It does not identify a physical mechanism. It does not make predictions that can be tested in the way that standard physics theories can be tested. It essentially says, the fine-tuning is real, it is not explained by any deeper law, and it exists because we are here. That is a philosophical answer, wearing the clothes of a scientific one, and many physicists find it unsatisfying in a way that is difficult to fully articulate, but impossible to ignore. The situation with dark energy gets even more interesting and more unsettling when you consider recent developments. The standard model of cosmology treats the cosmological constant as exactly that, a constant, a fixed value, the same everywhere and at all times. But recent observations have begun to hint that dark energy may not be constant at all. In 2024, the Dark Energy Spectroscopic Instrument Collaboration released results suggesting, at a statistical significance of approximately 3 sigma, that dark energy may be evolving over time, that it was stronger in the past and is growing weaker, or that it changes in some other way that distinguishes it from a pure cosmological constant. If confirmed at higher statistical significance, this would rule out the simplest explanation for dark energy and require a dynamical energy field, something like what theorists call quintessence, pervading all of space. A field that has its own equations of motion, its own evolution, its own physical properties waiting to be understood. A dynamical dark energy field is in some ways more tractable than a pure cosmological constant because it invites the question of what the field is made of, what determines its behavior, what physical principles govern it. But in another way, it makes the mystery deeper, because a dynamical field requires an explanation for why it has the value it has today. why it is neither too large nor too small, why it is evolving at the rate it is. And none of those questions have answers in any current theoretical framework. You are not moving from mystery to understanding. You are moving from one layer of mystery to another. The universe is made mostly of something we cannot identify or explain, and our best tools for explaining physical phenomena fail completely when applied to it. You might be willing, at this point, to accept the strangeness of the large-scale universe, the dark matter and dark energy and the Hubble tension, as problems that are confusing and unresolved but that live at cosmic scales far removed from everyday human experience. The universe is big, you might reason, and big things have big mysteries. But what happens when the strangeness is not at the scale of galaxies or cosmological constants, but at the scale of individual particles, at the most fundamental level of reality that physics has yet reached? What happens when the weirdness is not out there, in the distant reaches of the cosmos, but here in the fabric of existence itself, at the level of the basic building blocks of matter? Because quantum mechanics, the theory that describes reality at its smallest scales, contains within it some of the most profoundly disturbing puzzles in all of human thought. And they are not just philosophical puzzles, they have experimental consequences. Let us start with the double-slit experiment, because it is the experiment that Richard Feynman once called the central mystery of quantum mechanics, the one that exposes the deepest, most irreducible strangeness of the quantum world. The setup is deceptively simple. You have a source of particles, electrons, photons, atoms, or even molecules, and you fire them at a barrier with two narrow slits cut into it. Behind the barrier is a detector screen that records where the particles land. If particles behaved like classical objects, like tiny bullets, you would expect the detector screen to show two bright bands directly behind the two slits, the accumulated impact points of particles that pass through one slit or the other. And if you close one slit and fire particles through the other, that is exactly what you see. One band behind the open slit. But when both slits are open and you fire particles one at a time, one particle, then another, with enough time between them that there is never more than one particle in flight at once, something impossible happens. The particles do not accumulate into two bands. They accumulate into an interference pattern, a series of alternating bright and dark bands, exactly the kind of pattern produced by waves that pass through both slits simultaneously and interfere with each other, amplifying where they are in phase and canceling where they are out of phase. The particles are interfering with themselves, as if each individual particle passes through both slits at once, interferes with its own possible paths, and only then arrives at the detector. A single particle, traveling alone through space, somehow explores multiple possible trajectories simultaneously and produces a pattern that only makes sense if it took all of them. Now, here is where it gets deeper. If you place a detector near the slits, any detector, any physical device that can in principle determine which slit the particle went through, even if you never actually look at the data, the interference pattern disappears. Not because the detector disturbs the particle in some crude, mechanical way. Because the very possibility of knowing which path the particle took destroys the quantum interference. The act of making the path information available, even if no one ever reads it, collapses the particle's behavior from quantum to classical. The interference pattern is gone. Two bands behind the slits. The moment the universe contains a physical record of which path was taken, the particle stops behaving as if it took all paths at once. What this experiment is telling you, stripped of all the mathematical formalism, is something almost impossible to hold in your mind without it slipping away. Reality, at the quantum level, does not consist of definite things happening in definite ways. Before measurement, before the establishment of a physical record, there is only a superposition of possibilities. A smeared, unresolved cloud of potential outcomes, each with its own probability amplitude. The world of definite classical facts that you inhabit emerges from this quantum substrate only when information becomes physical, only when the quantum system interacts with its environment in a way that establishes records. Before that, the particle is not in one place. It is not in two places. It is in a quantum state that is incompatible with any classical description of location at all. The double-slit experiment is not a strange quirk. It is a window into the fundamental nature of physical reality. The implications cascade outward from this central fact in ways that physicists have spent nearly a century arguing about without reaching consensus. If quantum mechanics is taken literally, if the Schrödinger equation, which governs the evolution of quantum states, is truly the complete and fundamental description of reality, then every time a quantum measurement is made, every time a superposition interacts with a classical measuring device, the universe does not simply choose one of the possible outcomes. Instead, the entire system, particle, detector, experimenter, laboratory, planet, and ultimately everything connected to everything else, evolves into a superposition of all possible outcomes simultaneously. You do not observe the particle go left or go right. The universe branches. In one branch, you observe it go left. In another branch, an equally real version of you observes it go right. Both branches exist. Both are real. The universe is constantly, every instant, at every quantum interaction everywhere in space, branching into a vast branching tree of equally real parallel realities. This is the many worlds interpretation of quantum mechanics, proposed by Hugh Everett in his 1957 doctoral thesis. It is not a fringe idea. It is taken very seriously by a significant fraction of physicists who work on the foundations of quantum mechanics, including some of the most mathematically sophisticated. It makes the same experimental predictions as every other interpretation of quantum mechanics. That is both its strength and its epistemological challenge, since no experiment can currently distinguish between interpretations. But if it is correct, it carries implications about the nature of reality that are staggering in their scope. Every choice you have ever made has a quantum basis somewhere in the chain of physical causation. Every possible outcome of every quantum event has occurred in some branch of the universal wave function. The universe is not a single story. It is every story, all of them, simultaneously real, expanding outward through the tree of possibilities with every passing nanosecond. But even if you reject many worlds, even if you prefer one of the other interpretations of quantum mechanics, each of which has its own profound difficulties, the strangeness does not go away. It merely takes a different form. In the Copenhagen interpretation, the standard textbook version, the wave function collapses when a measurement is made. But there is no physical account of what causes this collapse or how it happens. The collapse is simply postulated. It is a rule added to the theory by hand, without being derived from anything deeper. In Bohmian mechanics, particles have definite positions at all times, guided by a hidden pilot wave, but that wave is non-local. It can instantaneously influence particles regardless of the distance between them, in apparent tension with the spirit of relativity. In the relational interpretation, there is no universal state of reality at all. Only relative facts, defined between systems with no observer-independent description of what exists. Every interpretation preserves the empirical predictions of quantum mechanics. None provides a comfortable, intuitive picture of what reality fundamentally is. And then there is entanglement. Quantum entanglement is perhaps the most philosophically troubling aspect of quantum mechanics, because it directly challenges one of the deepest intuitions we have about reality: that distant things are independent, that what happens here does not instantaneously affect what happens there, that the universe is local. When two particles interact in the right way and then separate, they can become entangled, linked in a quantum correlation that persists regardless of the distance between them. The quantum state of each particle is not independent, but is defined only in relation to the other. When you measure one particle and find it in a definite state, you instantly know the state of its entangled partner, wherever in the universe it happens to be, not because a signal has traveled between them, but because the measurement on one particle has instantaneously determined the joint state of both. Einstein hated this. He called it spukhafte Fernwirkung, spooky action at a distance, and he spent the latter part of his life trying to prove that it did not actually reflect a fundamental feature of reality. Together with Boris Podolsky and Nathan Rosen, he argued in a famous 1935 paper that quantum mechanics must be incomplete, that the correlations between entangled particles must be explained by hidden local variables, predetermined properties that the particles carry with them like hidden instructions, written at the moment of their interaction, telling each one how to respond when measured. The correlations would not be spooky at all. They would simply reflect pre-agreed outcomes, like two people who each take one glove from a pair. When the first person opens their bag and finds the left glove, they instantly know the other person has the right one, not because of any non-local influence, but because of what was determined at the start. In 1964, physicist John Bell showed that Einstein's intuition, however physically appealing, could be tested. He derived a set of inequalities, now called Bell inequalities, that any theory of hidden local variables must satisfy. If quantum mechanics, with its non-local entanglement correlations, violates those inequalities, then no hidden local variable theory can reproduce quantum mechanical predictions. The test was performed experimentally, most definitively in the 1980s by Alain Aspect and his collaborators, and has been performed many times since with steadily improving precision and closing of potential loopholes. The result is unambiguous. Quantum mechanics violates Bell's inequalities. The correlations between entangled particles are stronger than any local hidden variable theory can produce. The universe is non-local. What happens to one particle can be instantaneously correlated with what happens to another, regardless of the distance between them. This does not violate special relativity in the sense of allowing faster-than-light signaling. You cannot use entanglement to send information instantaneously, because the outcome of a quantum measurement is random, and you have no control over which result you get. But it does mean something profound and disturbing. The universe cannot be described as a collection of independent local objects, each carrying its own definite properties, interacting only through local, propagating influences. The world is not separable in that way. Distant parts of the universe are correlated in a manner that no classical, local, realistic picture of reality can accommodate. The very notion of a locally definite, independently existing physical reality, the bedrock assumption of every pre-quantum physics, has been experimentally falsified by a laboratory experiment. The universe has told us in the clearest possible terms that it is not the kind of thing we thought it was. At this point, you might be experiencing something that is difficult to name. It is not quite anxiety, not quite confusion, not quite wonder. It is something that sits at the intersection of all three. A growing awareness that the ground beneath your intellectual feet is not as solid as you assumed it was. You have looked at the universe at the largest scales and found that 95% of it is a mystery. You have looked at the rate at which it is expanding and found that the two best methods for measuring it give incompatible answers. You have looked at the smallest scales of reality and found that particles behave in ways that defy any classical intuitive picture of what physical existence means. Each of these anomalies, taken individually, might be filed under fascinating problems for future science. But together, they begin to suggest something more troubling, that the frameworks we have built to understand reality may be approaching, or may have already reached, their limits. The Standard Model of particle physics is another monument to human intellectual achievement that has begun to show its own particular strains. Developed over the latter half of the 20th century, the Standard Model describes all known fundamental particles and three of the four fundamental forces: the electromagnetic force, the weak nuclear force, and the strong nuclear force, within a single mathematical framework known as quantum field theory. It has been tested to extraordinary precision. The Higgs boson, the last missing piece of the Standard Model, was discovered in 2012 at the Large Hadron Collider at CERN, one of the greatest experimental triumphs in the history of physics. The Standard Model has never, in 50 years of increasingly precise experimental tests, been definitively falsified. It is extraordinarily successful, and Yet everyone in physics knows the Standard Model is not the final answer. It does not include gravity. It cannot explain the masses of the neutrinos, which we now know are not massless as the original formulation assumed. It has 19 free parameters, numbers like the masses of the fundamental particles and the strengths of the fundamental forces, that are not derived from any deeper principle, but are simply measured and inserted by hand. A truly fundamental theory would explain why those numbers are what they are. The Standard Model does not. It contains them the way a recipe contains its ingredients. They are given, not derived, and no one knows why the universe chose those particular values rather than any other. The electron is about 1,136 times lighter than the proton. Why? The strong force is about 100 times more powerful than the electromagnetic force at nuclear scales. Why? The three families of quarks and leptons have masses that span an enormous range, with no apparent pattern or organizing principle. Why? Beyond these internal puzzles, there is the persistent failure over several decades of the Large Hadron Collider and other experiments to find the new physics that theoretical physicists expected to find. The most popular candidate for physics beyond the Standard Model, a framework called supersymmetry, or SUSY, predicted the existence of a host of new particles, the supersymmetric partners of each known particle, with precisely defined properties. Supersymmetry was theoretically compelling because it solved several of the Standard Model's problems, including a particularly acute one called the hierarchy problem, the puzzle of why the Higgs boson is so much lighter than the Planck scale, the fundamental scale of quantum gravity. Supersymmetric particles were predicted to show up at the energy scales accessible to the LHC. The LHC has been running for years, at the highest energies ever achieved in a particle collider, and not a single supersymmetric particle has been found, not one. This absence is not a small disappointment. It has genuinely shaken the theoretical physics community's confidence in the research program of the past 40 years. A large fraction of the theoretical progress in physics since the 1970s has been built, directly or indirectly, on the assumption that supersymmetry is a feature of nature. String theory, the most ambitious attempt to unify all the forces and particles of nature into a single, theoretical framework, requires supersymmetry for its mathematical consistency. Without supersymmetric particles showing up at the energy scales where they were most naturally expected, the experimental foundation upon which decades of theoretical speculation rested has simply not materialized. The LHC has pushed its energy limits, increased its luminosity, and refined its analyses. The new particles are not there. This does not prove that supersymmetry is wrong. The supersymmetric particles could be heavier than the LHC can currently probe, hiding at energy scales beyond current reach. But the fact that they are not where the most natural and elegant versions of the theory predicted them to be, and the fact that with each run of the LHC, the allowed parameter space for supersymmetric theories shrinks further, forces a reckoning. The universe, once again, is not cooperating with our most beautiful theories. It is not providing the signals we expected. And when a theory is continually extended and modified and its parameter space is continually rearranged in order to stay consistent with the absence of the predictions that originally motivated it, the theory is starting to lose its explanatory power. It is starting to describe what cannot be rather than predict what will be. The muon anomalous magnetic moment is a specific example of a measurement that might be pointing beyond the Standard Model in a different direction. The muon is a heavier cousin of the electron, and like the electron, it has a magnetic moment, a tiny internal magnet, whose magnitude is slightly different from the value predicted by the simplest version of quantum mechanics. This deviation, called the anomalous magnetic moment, is produced by the constant interaction of the muon with the quantum foam of virtual particles surrounding it, and it can be calculated with extraordinary precision from the Standard Model. It can also be measured with extraordinary precision in laboratory experiments. For years, experiments at Brookhaven National Laboratory had measured a value for the muon's anomalous magnetic moment that was slightly higher than the Standard Model prediction, a discrepancy of about 3 to 4 sigma, tantalizing but not quite conclusive. In 2021 and subsequent years, the muon G2 experiment at Fermilab confirmed and strengthened that discrepancy, reaching a combined significance of over 4 sigma. Something beyond the standard model, some new particle, new field, new interaction, may be contributing to the muon's magnetic moment. The standard model is not completely accounting for the muon's behavior. Combine this with the W boson mass measurement made by the CDF collaboration at Fermilab in 2022, which found a value for the W boson mass significantly higher than the standard model prediction. A discrepancy of 7 sigma, an extraordinary degree of statistical significance. And the picture of a standard model under stress becomes harder to dismiss. Whether these anomalies will ultimately be confirmed by other experiments, whether they will resolve into a definitive discovery of new physics, or dissolve into systematic errors upon further scrutiny, remains to be seen. Science is a process, not a verdict. But the pattern is noteworthy. Anomalies in precision measurements of fundamental particles, in the expansion rate of the universe, in the rotation curves of galaxies, in the nature of 95% of the universe's contents. Everywhere we look with sufficient precision, something does not add up. Let us zoom out now from the specific anomalies and consider what they have in common, because there is a thread that connects them, a single intellectual problem that underlies all of them, and grasping that problem changes how you see everything. The deepest challenge of modern physics is not any one of these anomalies in isolation. It is the fact that our two most successful theories of nature, general relativity and quantum mechanics, are incompatible with each other in a way that goes to the very foundations of each. They do not just disagree on specific predictions, they disagree on the nature of reality itself. And that incompatibility, that fundamental conceptual tension at the heart of physics, may be the source of all the other anomalies, the root from which all the other strange fruits grow. General relativity is a theory of smooth, continuous space-time. In Einstein's framework, space and time are a fabric, a manifold in mathematical language, that is differentiable and continuous at all scales. There are no smallest lengths or shortest time intervals in general relativity. The fabric of space-time is infinitely divisible. Gravity is the curvature of this smooth, continuous fabric, and the behavior of matter and energy in this fabric is described by differential equations that assume continuity. If you zoom in on any region of space-time, no matter how small, it always looks smooth. Quantum mechanics is built on entirely different foundations. In quantum mechanics, energy comes in discrete packets, quanta. The states of quantum systems are described by vectors in abstract mathematical spaces called Hilbert spaces. Physical quantities are represented by operators that act on those vectors. The evolution of quantum states is governed by the Schrödinger equation, a linear, deterministic equation until measurement occurs, at which point something non-linear and stochastic happens, something that the formalism of quantum mechanics does not fully describe. There is no space-time manifold in quantum mechanics. Space and time play the role of background parameters, labels for positions and moments, but they are not dynamical objects. They do not curve, evolve, or interact with matter in the quantum mechanical formalism. They are just there as a fixed backdrop. When you try to combine these two frameworks, when you try to write a theory of quantum gravity, a quantum mechanical description of space-time itself, you run into mathematical catastrophes. The most straightforward approach, quantizing gravity using the same methods that work for the other forces, produces infinities at every turn. The calculations are not just difficult, they are undefined. The integrals that should give you finite answers for physical quantities instead diverge, racing off to infinity in a way that cannot be renormalized away using the tricks that work for quantum, electrodynamics, and the other standard model forces. Gravity simply does not respond to the standard tools of quantum field theory. At the extreme scales where both quantum mechanics and gravity should both be important, at the Planck length, about 10 to the power of negative 35 meters, and the Planck time, about 10 to the power of negative 44 seconds, our current theories of physics break down completely. They give no answer. They simply stop working. String theory was developed in large part as an attempt to resolve this conflict, to provide a mathematical framework that naturally incorporates both quantum mechanics and gravity in a single consistent structure. In string theory, the fundamental entities are not point particles but tiny vibrating strings of energy, whose different modes of vibration correspond to the different fundamental particles. When string theory is formulated consistently, it requires the existence of extra spatial dimensions beyond the three we observe, either 10 or 11 dimensions depending on the version, with the extra dimensions curled up at scales too small to be directly detected. String theory naturally contains a massless spin 2 particle in its spectrum, and such a particle in quantum field theory necessarily mediates a gravitational force with the properties of Einstein's general relativity. String theory does not just include gravity. It seems to require it to have gravity built into its mathematical DNA. But string theory has a profound problem. It is not a single theory. It is a vast landscape of possible theories, an estimated 10 to the power of 500 possible configurations, each corresponding to a different way of compactifying the extra dimensions, each predicting a different set of physical laws, different particle masses, different coupling constants, different values of the cosmological constant. Most of these configurations have nothing to do with the universe we actually inhabit. Finding the specific configuration that corresponds to our universe, the one that predicts the particular masses and forces and cosmological constant that we observe, turns out to be an enormously difficult problem. No one knows how to identify it from within the theoretical framework itself. No one knows what selects our particular configuration from the vast space of possibilities. And without that selection principle, string theory makes no specific predictions that differ from those of the Standard Model or general relativity. It is a vast, mathematically beautiful structure that currently cannot tell you anything about the universe that you could not already calculate from the theories it was supposed to supersede. This does not mean string theory is wrong. It might be right. It might be the correct description of the deepest level of physical reality, the theory that unifies everything, and we might simply lack the mathematical tools to extract its full predictions. But after 50 years of work by some of the most brilliant mathematical physicists alive, the theory still lacks a single confirmed experimental prediction that was not already predicted by the Standard Model or general relativity. Some physicists argue that this is simply because string theory operates at energy scales far beyond what any conceivable experiment could probe. Others argue that a theory with no accessible predictions is, by the standards of empirical science, not yet a scientific theory in the traditional sense. This is an argument about the nature of science itself, about what it means for a theory to be scientific. And it is happening right now, in the pages of physics journals and at conferences, and in academic hallways, among the people whose life's work is to understand the universe. There is another anomaly, quieter than the Hubble tension, less dramatic than quantum non-locality, but in some ways the most philosophically disturbing of all, that does not get the attention it deserves. It is called the black hole information paradox, and it sits at the precise intersection of quantum mechanics and general relativity, in the domain where the two theories are most incompatible, and it presents a contradiction that, if real, would require one or both of the most successful theories in physics to be fundamentally revised. A black hole forms when a massive star collapses under its own gravity at the end of its life. The gravitational force becomes so intense that nothing, not matter, not light, can escape once it passes a boundary called the event horizon. Within the event horizon, the curvature of spacetime becomes so extreme that all paths through spacetime lead inexorably toward the singularity at the center, where the density of matter is infinite and the laws of physics as currently formulated cease to apply. Black holes are among the most dramatic objects in the universe, and they present a direct confrontation between general relativity, which predicts the geometry of the black hole spacetime, and quantum mechanics, which governs the behavior of the matter and energy involved. In 1974, Stephen Hawking made one of the most remarkable theoretical discoveries in 20th century physics. Using a semi-classical approximation, treating the space-time geometry of the black hole classically according to general relativity, while treating the quantum fields in that space-time according to quantum mechanics, he found that black holes are not truly black. They emit radiation. The quantum vacuum near the event horizon is disturbed by the extreme space-time curvature in a way that produces a thermal spectrum of radiation, now called Hawking radiation, with a temperature inversely proportional to the mass of the black hole. This radiation carries energy away from the black hole, reducing its mass. Over an enormously long period of time, for a stellar mass black hole, far longer than the current age of the universe, the black hole will completely evaporate, its mass entirely converted into Hawking radiation and radiated away into the cosmos. This discovery is beautiful and important, but it creates a devastating paradox when you ask the following question: what happens to the information about the matter that fell into the black hole? In quantum mechanics, information is never destroyed. The quantum state of a physical system evolves according to the Schrödinger equation, which is time reversible and unitary. If you know the current state of a quantum system, you can in principle reconstruct its entire past history and predict its entire future with complete precision. Information is conserved. This is not just a rule that quantum mechanics happens to follow. It is one of the deepest structural features of the theory, related to the probability interpretation and the consistency of quantum mechanics itself. If information is not conserved, quantum mechanics breaks down. But Hawking's calculation suggests that the Hawking radiation emitted by a black hole is perfectly thermal. It has no structure beyond its temperature, carrying no information about what fell into the black hole. A black hole formed by the collapse of a star made of hydrogen radiates exactly the same Hawking radiation as a black hole of the same mass formed by the collapse of a star made of gold, or of pure information, or of any other kind of matter. The outgoing radiation has no memory of the infalling matter. When the black hole completely evaporates, all the information about its contents appears to be gone, reduced to a featureless thermal bath. But quantum mechanics says information cannot be destroyed. So either quantum mechanics is wrong, or Hawking's calculation is wrong, or general relativity, specifically its treatment of the event horizon as a smooth, unremarkable region of space-time through which information simply falls, is wrong in some subtle but crucial way. This trilemma is the black hole information paradox. Hawking himself initially argued that information truly is destroyed in black hole evaporation, and that quantum mechanics must be modified to allow this. Most quantum field theorists found this unacceptable and argued that information must somehow be encoded in the Hawking radiation, even if Hawking's approximate calculation does not show it. In 1997, Juan Maldacena discovered a profound connection between certain quantum gravity theories and quantum field theories, the AD-S-CFT correspondence, which provides strong theoretical evidence that information is indeed preserved in black hole evaporation. The information somehow gets encoded in the Hawking radiation, in correlations so subtle and complex that they are essentially invisible to any practical calculation, but they are there. This is currently the majority view. But the resolution of the paradox is not without its own cost. In recent years, a proposal called the firewall hypothesis has emerged, suggesting that the way information is preserved in Hawking radiation requires the event horizon of a black hole to be a dramatic, energetic boundary, a firewall of high-energy radiation, rather than the smooth, unremarkable region that general relativity predicts. If the firewall hypothesis is correct, then an astronaut falling into a black hole would not smoothly cross the event horizon and continue floating inward, as general relativity predicts, but would instead be instantly incinerated at the horizon. This is in direct contradiction with one of the fundamental principles of general relativity, the equivalence principle, which states that a freely falling observer should feel no local effects at the event horizon of a large black hole. If the firewall is real, the equivalence principle is violated. General relativity is wrong in a regime where it should be valid. The black hole information paradox and its proposed resolutions are telling you something very important. At the boundary between quantum mechanics and general relativity, something has to give. Both theories cannot be simultaneously right in their current forms, in the regimes where they both apply. One or both must be modified, must be subsumed into a deeper theory that reduces to general relativity in the appropriate limit and to quantum mechanics in its appropriate limit. But that differs from both in the extreme situations where they both apply and contradict each other. And we do not have that deeper theory. We do not know what it looks like. We do not know what principles it will be built on. We only know that something deep, something structural, something foundational must change. Now let us move into territory that is more speculative, but no less grounded. Territory where the anomalies and paradoxes of physics begin to shade into deeper questions about the nature of reality, about what the universe actually is at its most fundamental level, about whether the categories of thought we use to describe the world are adequate to the task of describing it. Because there is a limit, and it is becoming increasingly clear that we may be approaching it, to how far the current framework of physics, the cosmological constant in quantum field theory, has a natural interpretation. Quantum mechanics tells us that empty space is not truly empty. It is a seething, roiling foam of virtual particles, pairs of matter and antimatter that pop in and out of existence for vanishingly brief moments, borrowing energy from the vacuum and returning it before the universe has time to notice. These quantum fluctuations contribute energy to the vacuum, and that vacuum energy is the natural candidate for the cosmological constant. When quantum field theorists calculate the expected energy density of the vacuum from first principles, adding up all the contributions from all the known quantum fields, they arrive at a number, a specific, calculable prediction for how large the cosmological constant should be. And when you compare that theoretical prediction to the observed value of the cosmological constant, as measured from the accelerating expansion of the universe, you find a discrepancy that is so enormous, it is almost impossible to convey in ordinary language. The theoretical prediction exceeds the observed value by a factor of approximately 10 to the power of 120. That is a 1 followed by 120 zeros. In all of physics, in all of science, in all of human intellectual history, there has never been a theoretical prediction that was this wrong. Not even close. The standard tools of quantum field theory, applied to the simplest and most natural estimate of vacuum energy, give an answer that is so catastrophically, absurdly larger than what we observe that the discrepancy cannot be a rounding error or a small overlooked factor. Something is canceling almost all of the vacuum energy, reducing it from the enormous value that quantum field theory predicts to the tiny value we actually observe, with a precision of 120 decimal places. That level of cancellation, if it is the result of some underlying mechanism, requires that mechanism to be tuned to 1 part in 10 to the 120th. That is fine-tuning of an almost unfathomable degree. This is known as the cosmological constant problem, and it has been described by physicists as the worst problem in theoretical physics, the most embarrassing failure of any theoretical framework to agree with observation. It is not a small error in a peripheral calculation. It is a catastrophic failure of our best physical theories when applied to one of the most fundamental questions about the universe. Why is the energy of empty space the value that it is? The problem was recognized in the late 1980s and has been a central puzzle of theoretical physics ever since. Enormous effort has been devoted to it. The proposed solutions fill entire textbooks, and none of them are satisfying. None of them have achieved consensus. None of them have been confirmed by experiment or observation. One of the most discussed proposed solutions is called the anthropic principle, which has a long and somewhat uncomfortable history in physics. In the context of the cosmological constant, the anthropic argument goes roughly like this. There may be an enormous number of universes, a multiverse, each with a different value of the cosmological constant, distributed randomly, across a vast landscape of possibilities. In most of those universes, the cosmological constant is so large and positive that the universe expands so rapidly that matter never has time to clump together into galaxies, stars, and planets. Life cannot form. No one is there to observe anything. But in a small subset of universes, the cosmological constant happens, by chance, to be small enough that structures can form, stars can ignite, planets can coalesce, and beings can evolve who look up at the sky and wonder about the nature of reality. We find ourselves in one of those rare structure-permitting universes simply because we could not exist in any other kind. The cosmological constant is small, not because of any deep physical mechanism, but because small is the only value consistent with our existence. This argument, championed by physicists like Steven Weinberg, who made a quantitative prediction of the maximum allowed value of the cosmological constant on anthropic grounds before the year 1998 supernova results, and whose prediction was remarkably close to the value eventually measured, is intellectually serious. It is not the domain of crackpots, but it is deeply uncomfortable for many physicists because it is not, in the traditional sense, an explanation. It does not identify a physical mechanism. It does not make predictions that can be tested in the way that standard physics theories can be tested. It essentially says, the fine-tuning is real. It is not explained by any deeper law, and it exists because we are here. That is a philosophical answer wearing the clothes of a scientific one, and many physicists find it unsatisfying in a way that is difficult to fully articulate, but impossible to ignore. The situation with dark energy gets even more interesting and more unsettling when you consider recent developments. The standard model of cosmology treats the cosmological constant as exactly that, a constant, a fixed value, the same everywhere and at all times. But recent observations have begun to hint that dark energy may not be constant at all. In 2024, the Dark Energy Spectroscopic Instrument Collaboration released results suggesting, at a statistical significance of approximately 3 sigma, that dark energy may be evolving over time, that it was stronger in the past and is growing weaker, or that it changes in some other way that distinguishes it from a pure cosmological constant. If confirmed at higher statistical significance, this would rule out the simplest explanation for dark energy and require a dynamical energy field, something like what theorists call quintessence, pervading all of space. A field that has its own equations of motion, its own evolution, its own physical properties waiting to be understood. A dynamical dark energy field is in some ways more tractable than a pure cosmological constant because it invites the question of what the field is made of, what determines its behavior, what physical principles govern it. But in another way, it makes the mystery deeper, because a dynamical field requires an explanation for why it has the value it has today, why it is neither too large nor too small, why it is evolving at the rate it is. And none of those questions have answers in any current theoretical framework. You are not moving from mystery to understanding. You are moving from one layer of mystery to another. The universe is made mostly of something we cannot identify or explain, and our best tools for explaining physical phenomena fail completely when applied to it. This is the kind of statement that sounds like wordplay until you realize that the experiment has been performed and the results are real, and the interpretation is not wordplay, but the straightforward reading of what the data shows. The universe does not simply unfold from past to present, with the past being fixed and the future open. At the quantum level, even the past has a kind of openness, a kind of incompleteness that is resolved only by interactions in the present. Causality, the principle that the past determines the future and not the other way around, still holds in a macroscopic, statistical sense. But at the fundamental level of individual quantum events, the relationship between past and future is more symmetric, more entangled, more strange than our classical intuitions suggest. At some point in this journey, you have to confront a possibility that most scientific discussions carefully avoid, because it sits at the uncomfortable boundary between physics and philosophy, between legitimate inquiry and speculation that has not yet earned the right to be taken seriously. but it has been earning that right, slowly, over the past several decades, as developments in physics and cosmology and computer science have given it increasing theoretical traction. The possibility is this: the universe you inhabit may not be the fundamental level of reality. It may be a structure running on top of something else, something deeper, something that does not share the properties of physical space and time that you experience as irreducibly basic. The universe may be, in some sense, that is not yet fully defined, but is increasingly taken seriously, computational, informational, a simulation. Before you dismiss this as science fiction, let us approach it carefully, because the arguments for taking it seriously come not from science fiction authors, but from philosophers, physicists, and mathematicians working at the frontiers of their fields. The simulation hypothesis, in its most careful, academically discussed form, does not claim that someone in a computer lab somewhere is running the universe on a machine made of transistors. The claim is more precise and more disturbing. If it is in principle possible for a physical system to simulate another physical system, including systems that contain conscious observers, then the total number of simulated universes that could in principle exist is vastly larger than the number of physical universes. And if you are an observer with no direct access to the underlying layer of reality, if you can only experience the reality you find yourself in from the inside, then statistically, you are almost certainly in one of the simulated ones rather than in the base physical reality. This argument, formalized by philosopher Nick Bostrom in his 2003 trilemma, has been discussed seriously by physicists including Max Tegmark, by cosmologists, and by some of the wealthiest and most scientifically literate people in the technology industry, several of whom have publicly stated they believe it is likely, or at least plausible, that we live in a simulation. That fact does not make it true. Appeal to authority is not a scientific argument, but it does suggest that the idea is not as easily dismissed as it initially appears. And here is the thing that makes it genuinely interesting from the perspective of physics. If the universe is a computational process, then some features of physics that currently seem mysterious or arbitrary might have natural explanations in terms of the computational substrate. The fact that physical quantities are quantized, that energy and angular momentum and charge come in discrete, indivisible units, might reflect the discrete digital nature of a computational substrate. The fact that the speed of light is finite and invariant might reflect a maximum clock speed in the underlying computation. The fact that the laws of physics are mathematical, that the universe seems to be described by elegant equations, might reflect the fact that it is fundamentally a mathematical object, a structure running according to programmed rules. The fine-tuning of the physical constants, the fact that the values of the constants of nature seem precisely calibrated to allow the existence of complexity, life, and consciousness, might reflect not deep anthropic coincidence or multiverse selection, but deliberate design, in the way that a video game world is designed to be interesting and traversable rather than randomly inhospitable. These are not proofs. They are consistencies. They are observations that, while not confirming the simulation hypothesis, are at least consistent with it, in a way that deepens the puzzle rather than resolving it. Physicist Silas Bean and colleagues have even proposed a potential observational test of the simulation hypothesis. If the universe is being simulated on a computational lattice, a discrete grid of spacetime points, then there might be observable signatures of that discreteness at extremely high energies, in the form of an anisotropy in the distribution of ultra-high energy cosmic rays, which would be preferentially deflected along the axis of the computational lattice. The test has not yet been performed at sufficient precision to draw conclusions. But the fact that a potential observational signature can even be proposed suggests that the simulation hypothesis has crossed a threshold from pure speculation into the domain of, at least in principle, empirically testable ideas. There is also a deeper version of the same basic intuition, formalized by physicist Max Tegmark as the mathematical universe hypothesis. Tegmark argues that the universe is not merely described by mathematics, it is mathematics. Every mathematical structure that is logically self-consistent has an equally real physical existence. The universe we inhabit is one such mathematical structure, one of infinitely many, all equally real. We find ourselves in this particular structure because it is one of the structures complex enough to contain observers who can ask the question of what kind of universe they inhabit. On this view, the deepest fact about reality is not physical, it is mathematical. The universe does not exist in space and in time with mathematical structure imposed on top. It is the mathematical structure all the way down, with no further physical stuff underlying it. This idea might seem too abstract to be taken seriously, but it has a profound implication that makes it more than idle philosophizing. It explains why mathematics is so unreasonably effective at describing physical reality. The physicist Eugene Wigner famously noted in a 1960 essay, "The unreasonable effectiveness of mathematics, the fact that mathematical structures invented with no empirical motivation whatsoever for purely abstract reasons, repeatedly turn out, sometimes decades later, to be precisely the right language for describing physical phenomena." Non-Euclidean geometry, developed in the 19th century as a purely mathematical exercise in what happens when you relax Euclid's parallel postulate, turned out to be the exact mathematical language needed to describe Einstein's curved spacetime. Group theory, developed as an abstract study of symmetry, turned out to be the precise framework needed to classify elementary particles and their interactions. Riemann surfaces, developed by mathematicians who had no idea they would ever be applied to physics, turned out to be central to string theory. If the universe is a mathematical structure, this unreasonable effectiveness is not mysterious at all. Mathematics works because the universe is made of it. But if the universe is mathematics, if reality at its deepest level is a self-consistent logical structure with no further physical substrate, then some of the anomalies we have been discussing take on a different character. The fine-tuning of physical constants, the cosmological constant problem, the hierarchy problem. These cease to be puzzles about a physical system whose parameters need explaining and become facts about a particular mathematical structure, selected from among the ensemble of all possible mathematical structures by anthropic reasoning or by some deeper principle of mathematical self-reference. The Hubble tension becomes a discrepancy in our mapping of a mathematical structure, perhaps indicating that our current model is an approximation to the true structure, valid in certain regimes, but failing in others. The quantum measurement problem becomes the puzzle of how a single branch of mathematical possibility becomes the experienced reality of an observer embedded in the structure. None of these frameworks, the simulation hypothesis, the mathematical universe hypothesis, relational quantum mechanics, the many worlds interpretation, resolves the anomalies of physics in the way that the discovery of Neptune resolved the anomaly in Uranus's orbit. None of them gives you a new equation that you can use to calculate the Hubble constant more accurately or predict the properties of dark matter particles. They are not solutions in that sense. They are frameworks, ways of seeing the problem that might or might not point toward solutions, and they all share something important. They suggest that reality at its most fundamental level is radically different from the intuitive picture we build from everyday experience. Not just in the way that quantum mechanics or relativity is surprising, departing from classical intuition in specific, well-defined ways, but in a more profound sense, in the sense of challenging the very categories: space, time, matter, causality, existence, that we use to organize our experience of the world. Let us talk about time, because among all the concepts that physics deals with, time is the one where the gap between scientific description and human experience is most stark, most troubling, and most revealing of the depth of our confusion about reality. You experience time as a flow, a continuous directed progression from past to present to future, with the present being the special, vivid, immediate moment of existence, the past being fixed and unchangeable, the future open and undetermined. This experience of temporal flow, of the now, moving perpetually forward through time, is so fundamental to your existence that it is almost impossible to imagine experiencing the world without it. It is not just a feature of consciousness. It feels like the most basic fact about the world. Things happen, moments pass, time flows. Physics does not contain any of this. The fundamental equations of physics, both classical and quantum, both relativistic and non-relativistic, are time reversible. You can run them forward or backward, and the laws look the same. There is no built-in direction of time in the equations of motion, no preferred forward direction in which the laws say things must evolve. Newton's laws are time-symmetric. Maxwell's equations are time-symmetric. Quantum mechanics is time-symmetric. The Standard Model is almost perfectly time-symmetric, with only a tiny violation associated with the weak nuclear force, far too small to account for the overwhelming directionality of time we experience. General relativity treats time as just another dimension of the space-time manifold, different from the spatial dimensions in its signature, but still just a dimension, not a flow. The physicist Julian Barbour has argued, following an analysis of the structure of general relativity and the Wheeler-DeWitt equation of quantum gravity, that time does not flow at all. On his view, what we call time is simply a record of correlations between different configurations of the universe, different instantaneous states, each complete in itself, with no process of change connecting them. The experience of flow on Barbour's account is an illusion generated by the fact that any complex configuration of the universe that contains an observer will also contain records of past configurations, memories, and the experience of moving through time is just the observer parsing those records, finding themselves embedded in a sequence of correlated snapshots. But the snapshots do not unfold. They simply are. All of them, simultaneously. The entirety of cosmic history, every moment from the Big Bang to the heat death of the universe, exists as a static, unchanging mathematical object, the block universe, and what you experience as now is just your location within that object, your position in the four-dimensional landscape. The block universe interpretation of space-time is not fringe physics. It is the most literal reading of special relativity, which implies that simultaneity is relative. What is now for you depends on your state of motion. Two events that are simultaneous in your reference frame are not simultaneous in the reference frame of someone moving relative to you. There is no universal, reference frame independent now. The present moment is not a cosmic fact. It is a local, frame-dependent artifact. In the block universe, all moments of time are equally real. The past is not gone, the future is not yet to come. They are just different positions along the temporal dimension, as real as different positions in space. You do not move through time. You are located at a particular temporal position, and the experience of movement is generated by the complex, memory-laden nature of the configurations at each position. If this is true, and the physics of special relativity gives it strong support, then the most intimate feature of your experience, the one thing you feel most certain about, the ceaseless forward flow of time, is not a feature of physical reality. It is a feature of the way your particular configuration, your brain, your memories, your biochemistry, processes the information available to it. The flow of time is something you construct, not something you find. And the question of why you construct it, why your subjective experience has a direction that the fundamental physics does not, is called the arrow of time problem, and it is one of the deepest unsolved problems in all of physics and philosophy combined. The second law of thermodynamics gives time its arrow at the macroscopic level. Entropy, the measure of disorder or the number of microstates consistent with a given macroscopic description, always increases with time. Eggs do not unscramble. Smoke does not re-enter a chimney. Ice cubes do not spontaneously reassemble from their melted puddles. The universe evolves from low entropy states to high entropy states, not the reverse, and this asymmetry is the physical basis for the directionality of time that we experience. But the second law is a statistical law, not a fundamental one. It holds because the number of high entropy states vastly outnumbers the number of low entropy states. So any system evolving randomly through its possible states will almost certainly move toward higher entropy. It does not follow from the fundamental time-symmetric laws of mechanics. It is an emergent, statistical phenomenon, and here is the deepest puzzle. For the second law to work, for entropy to have been increasing since the Big Bang, the universe must have started in an extraordinarily low entropy state. The Big Bang must have been a state of remarkable order, remarkable specificity, remarkable tidiness, from which the universe has been moving toward disorder ever since. But why? Why should the beginning of the universe be a state of such low entropy? There is no known physical law that demands this. It seems, from a statistical point of view, extraordinarily unlikely. As unlikely as shuffling a deck of cards and finding them perfectly sorted by suit and rank. In fact, far, far more unlikely than that. The initial low entropy of the universe is not explained by any current cosmological theory. It is simply assumed, inserted as an initial condition, because without it the second law does not work, and time has no arrow. The ordered, directed, irreversible experience of time that defines your entire existence rests on a fact about the early universe, an extraordinary, statistical improbability of its initial conditions that physics has no explanation for. Something happens to you psychologically when you follow these threads far enough. It is not panic, because the world continues to be what it is regardless of what the physics says. The apple still falls, the sun still rises, your coffee still gets cold. The familiar universe of macroscopic objects following predictable paths in three-dimensional space persists, as solid and reliable as it has always seemed. But something shifts in your understanding of what that reliability means. It begins to feel not like a window onto the nature of things, but like a very effective local approximation, a useful fiction that works within the domain of scales and energies relevant to human life, but that does not penetrate to the actual structure of reality. The map is not the territory, and the territory, it is now becoming clear, is something stranger and more resistant to comprehension than any map we have yet drawn. There is a concept in physics called the effective field theory framework, and understanding it changes how you relate to scientific knowledge. An effective field theory is not a fundamental description of nature. It is a description that is valid within a particular range of energies and scales, valid enough to make accurate predictions within that range, but explicitly not applicable outside it. The standard model of particle physics is an effective field theory. It works beautifully at the energy scales accessible to current experiments, but it breaks down at the Planck energy, where quantum gravity becomes important. Newtonian mechanics is an effective field theory valid at speeds much less than the speed of light, and at length scales much larger than the atom. General relativity is an effective field theory that breaks down at singularities. Every theory we have at every level is an effective description with a specific domain of validity beyond which it fails. This might seem like a reason for humility, a recognition that all knowledge is partial and provisional, which is something scientists have always acknowledged in principle. But it is more unsettling than mere humility, because it means that the universe contains regimes that are not described by any current theory. It contains the first instant of the Big Bang, where both quantum mechanics and general relativity apply simultaneously and both break down. It contains the interiors of black holes. It contains the very small scales at which space-time may have a granular or discrete structure, incompatible with its smooth Einsteinian description. These are not exotic hypothetical situations. They are real, physical, actual features of the universe we inhabit. And in those regimes, we are genuinely in the dark. Not in the dark in the way of not having finished a calculation, but in the dark in the way of not having any theoretical framework at all. The philosopher of science, Thomas Kuhn, in his 1962 book, The Structure of Scientific Revolutions, described how science does not progress by the smooth, linear accumulation of knowledge, but through periodic, discontinuous upheavals he called paradigm shifts. Normal science, Science conducted within an established paradigm, using its tools and concepts to solve puzzles within its framework, accumulates anomalies over time, observations and experimental results that do not fit the established framework. For a while, these anomalies are ignored or worked around. The framework is extended, patched, modified, but eventually, if the anomalies are deep enough and numerous enough, the framework can no longer accommodate them, and a crisis develops. A new framework emerges, typically from a young scientist who is not yet too deeply invested in the old one, that resolves the anomalies not by solving them within the old framework, but by dissolving them, reconceptualizing the entire problem in a way that makes the old framework's failures comprehensible as the result of working with incorrect foundational assumptions. The anomalies we have been exploring, the Hubble tension, dark matter, dark energy, the cosmological constant problem, the incompatibility of quantum mechanics and general relativity, the black hole information paradox, the measurement problem, the arrow of time, the fine-tuning of constants, the absence of supersymmetric particles, feel increasingly like the kind of anomaly accumulation that precedes a Kuhnian revolution. Not because scientists have given up on solving them within the current framework. They have not, and good science demands that you try every avenue within the established framework before abandoning it. But because the sheer number and diversity and depth of the anomalies is beginning to suggest that they may not all have separate, local explanations. They may all be symptoms of a single, deeper problem, a conceptual inadequacy at the foundation of the current framework that will require not a new parameter or a new particle, but a genuinely new way of thinking about what the universe is. What might that new way of thinking look like? This is where honesty requires acknowledging that we do not know. The next revolution in physics, if it is coming and the current state of the anomalies suggests that something must change, may be as unimaginable from our current vantage point as special relativity would have been unimaginable to Newton. Einstein did not just add corrections to Newtonian mechanics. He reconceived the nature of space, time, and motion from the ground up, using new conceptual tools, the space-time interval, the principle of equivalence, the geometric nature of gravity, that had no place in the Newtonian framework. The next revolution might require a reconception of equal depth, involving concepts we do not yet have names for, built on intuitions we have not yet developed, describing aspects of reality that our current conceptual vocabulary is not equipped to articulate. Some physicists believe that the key lies in the relationship between information and physical reality, that the next physics will be built on informational foundations rather than on space, time, matter, and force. John Archibald Wheeler's It from Bit and its modern descendant, the It from Qubit program of quantum information theorist John Preskill, suggest that space-time itself might be an emergent phenomenon arising from quantum entanglement, that the smooth, continuous geometry of general relativity is not fundamental, but emerges from the much more abstract structure of quantum information processing at the Planck scale. The geometry of space is not the starting point of the theory. It is the output, a consequence of the entanglement structure of the fundamental quantum degrees of freedom. This idea has gained significant support from developments in the ADS-CFT correspondence, where it has been shown that the geometry of the bulk spacetime can be reconstructed from the entanglement structure of the boundary quantum theory. Space emerges from entanglement. Geometry is information. Others believe the key lies in the nature of time, that time is not a fundamental feature of the universe but an emergent one, a statistical phenomenon that arises when complex systems with internal memory interact with each other. Lee Smolin has argued that only the present moment is real, that the block universe is wrong, that time genuinely flows, and that the laws of physics themselves evolve with time rather than being eternally fixed. This radical position, called temporal naturalism, is motivated by the observation that the laws of physics cannot be derived from anything more fundamental. They are simply given as brute facts about the universe, and that if time is real and physical laws can evolve, then perhaps the particular laws we observe are not eternal necessities, but contingent outcomes of cosmic history, selected by some form of cosmological evolution. The universe might not have begun with fixed laws. The laws might have crystallized out of a more lawless, chaotic beginning, becoming more orderly as the universe cooled and structured itself, just as the symmetries of physics are broken as the universe cools from the Big Bang's initial extreme temperatures. And there are those who believe the key lies in the nature of consciousness, who argue that the hard problem of consciousness, the question of why there is subjective experience at all, why there is something it is like to be a particular physical system, is not separable from the hard problems of physics. The physicist Roger Penrose has argued that consciousness involves quantum processes at the level of microtubules in neurons, and that the resolution of the quantum measurement problem and the understanding of consciousness are connected, that they will both require a new theory of physics that goes beyond standard quantum mechanics. Philosopher and cognitive scientist David Chalmers has argued that consciousness may be fundamental, not reducible to physical processes, but one of the basic features of reality, alongside mass and charge in space-time. On this view, a complete theory of reality must include consciousness among its fundamental ingredients, and physics without it is, by definition, incomplete. You might find some of these ideas compelling and others fanciful. Your reaction will depend on your temperament, your prior beliefs, your tolerance for radical reconceptualization. But here is what should strike you, regardless of which ideas you find most plausible. The fact that all of these proposals are being seriously discussed, that all of them are being developed mathematically and defended philosophically, and tested, to the extent possible, empirically, by serious and talented and rigorous thinkers at the frontiers of physics and philosophy, is itself a signal. It is a signal that the current framework is under stress from multiple directions. It is a signal that the boundaries of what counts as legitimate scientific inquiry are expanding, because the established framework is no longer fully adequate to contain the questions it has generated. And it is a signal that whatever comes next will not be a small adjustment. It will be a reconception of what the universe is. Let us return, for a moment, to the largest scale, to the universe as a whole, because there are features of the cosmos that, when you look at them in the right light, suggest something that goes beyond the specific anomalies we have discussed and implies a more general strangeness about the whole enterprise of cosmology. One of these features is something called the cosmological horizon problem. The cosmic microwave background, that ancient light from the early universe, is extraordinarily uniform in temperature across the entire sky. The temperature differences across different regions are less than 1 part in 100,000. This uniformity is remarkable to the point of being suspicious, and here is why. The regions of the sky that we observe in opposite directions were, at the time the CMB was emitted, so far apart from each other that they could not possibly have been in causal contact. Light, traveling at the maximum possible speed, could not have carried information between them in the time available since the Big Bang. They were, in the causal structure of the universe, completely disconnected. Yet they have essentially identical temperatures. How? The standard answer to this puzzle is cosmic inflation, a theory proposing that in the first tiny fraction of a second after the Big Bang, the universe underwent an extraordinarily rapid exponential expansion, during which a region so small that it was already in thermal equilibrium was blown up to a size vastly larger than the observable universe. The uniformity of the CMB is explained because all of it originated from a single, tiny, well-mixed region that was then stretched to cosmic scales by inflation. The theory of inflation, proposed by Alan Guth in 1980 and developed by Andre Linde and others, is elegant and powerful. It solves the horizon problem. It also solves the flatness problem, the puzzle of why the spatial geometry of the universe is so close to perfectly flat, which would be an extraordinarily fine-tuned initial condition without inflation. And it predicts the spectrum of fluctuations in the CMB, the pattern of temperature variations, with remarkable precision. Inflation is one of the most successful ideas in cosmology, but inflation has a deep theoretical problem, and it is one that is not often discussed outside the technical literature. The mechanism that ends inflation, the The transition from the exponentially expanding inflationary phase to the hot, radiation-dominated Big Bang is not well understood. In most inflationary models, the process of ending inflation, called reheating, requires specific dynamics of the inflatant field whose properties are not independently constrained. More fundamentally, in most inflationary models, inflation does not end everywhere simultaneously. Due to quantum fluctuations in the inflatant field, some regions of the universe stop inflating while others continue. The continuing regions expand and create more space, which then inflates further, with some subregions stopping and others continuing. This process, called eternal inflation, creates an infinite fractal of inflating and non-inflating regions, an infinite multiverse, each bubble universe having its own properties determined by the quantum fluctuations that ended inflation in that particular region. If eternal inflation is correct, then what we call the universe is just one bubble among an infinite sea of bubbles, each with different physical constants, different symmetries, different laws. And in an infinite multiverse, every possible bubble exists. Every possible combination of physical constants is realized somewhere. The question of why our universe has the particular physical constants it has, the fine-tuning problem, is answered by anthropic selection. We are in a bubble where the constants allow life because we could not be in a bubble where they do not. The cosmological constant, the Higgs mass, the strength of the fundamental forces, all are determined not by any deep physical principle, but by random quantum fluctuations. In the early inflation, selected by the fact that we are here to observe them. The universe is not fine-tuned by a designer or by a deep physical law. It is just one of infinitely many, and we are in a habitable one for the same reason that you find yourself on a planet with an atmosphere. Not because planets with atmospheres are special, but because you could not find yourself anywhere else. This is intellectually coherent. It may even be correct, but it has a price. It removes the universe from the domain of scientific explanation. If the values of the physical constants are determined by random processes in an eternal inflation scenario with no measurable consequences for the bubble we inhabit, then we cannot, even in principle, predict what those values should be from any theoretical framework. Science becomes, on the largest scale, a study of our local contingency rather than a revelation of deep, necessary truths. The universe is not lawful in the deep sense. It is accidental. Its laws are not eternal truths written into the fabric of reality. They are the local ordinances of one particular bubble among infinite others, no more necessary or universal than the particular language spoken in a particular city. This troubles many physicists deeply, not just aesthetically, but scientifically. Science is built on the assumption that the universe is, at its deepest level, explicable, that the laws and constants of nature are what they are for reasons that a sufficiently complete theory could reveal. If eternal inflation is true, and the physical constants are anthropically selected from a random distribution, then that assumption fails for the most fundamental questions. The deepest why of physics, why the Higgs mass is what it is, why the electron has its particular charge, why the cosmological constant is the tiny value it is, have no scientific answer. They have only anthropic non-answers. These are the values that permit life, and we are alive. The explanatory project of physics at its most fundamental level hits a wall. There is a concept developed by physicist and cosmologist Max Tegmark in another context that is relevant here: the measure problem of the multiverse. In an infinite multiverse, every possible observation is made by some observer. Every possible measurement yields every possible result in some bubble. The question of what we should expect to observe, the question that connects theory to observation and makes science possible, becomes undefined because there is no well-defined probability distribution over an infinite ensemble of universes without a measure, a way of assigning weights to different possibilities. And there is no agreed-upon, well-motivated measure for the multiverse. Different choices of measure give different predictions for what we should observe. The theory that was supposed to explain everything explains everything in a way that makes it impossible to confirm or falsify, because anything we observe is consistent with it. This is a subtle but important point. When cosmologists discuss the multiverse or eternal inflation or the large-scale topology of the universe, they are extrapolating their models far beyond the domain in which those models have been tested. The standard model of cosmology, the lambda CDM model, has been tested with extraordinary precision within the observable universe, and it works beautifully within that domain. But extending it beyond the observable horizon to infinite or near infinite scales requires assumptions about the uniformity and continuity of physical laws that cannot be verified. The universe might be infinite. It might have a complex topology that wraps back on itself. It might have radically different properties beyond the horizon. We simply have no way of knowing, and any claim about it is, strictly speaking, beyond the reach of empirical science. This is not a criticism of cosmology. It is a recognition of a fundamental epistemic boundary, a limit on what can be known from within any finite region of the universe, regardless of how good your instruments are or how sophisticated your theories become. The universe is larger than what can be observed. Knowledge is bounded by the horizon, and behind the horizon lies a territory that is, in the most literal sense, unknowable, not because of technological limitations that might someday be overcome, but because of the fundamental structure of space-time, which limits the propagation of information to the speed of light and limits the amount of time that has elapsed since the beginning. The observable universe is all we have. Everything beyond it is, epistemically speaking, a leap of faith in the extrapolation of theory. And even within the observable universe, there are limits. The Planck length, approximately 1.6 times 10 to the minus 35 meters, is the scale at which the quantum effects of gravity become important, where space-time itself may cease to be a smooth continuum and take on a granular or foam-like structure. Below the Planck length, our current theories give no description of reality whatsoever. The Planck time, approximately 5.4 times 10 to the minus 44 seconds, is the shortest time interval our current theories can meaningfully describe. Before the Planck time, in the very first instance of the Big Bang, our theories break down. The laws of physics, as currently formulated, do not tell us what the universe was doing before the Planck time. They simply do not apply. The beginning of the universe is, in a precise theoretical sense, inaccessible to current physics. So here is the full epistemic situation, laid out starkly. Below the Planck scale, theory breaks down. Beyond the observable horizon, empirical verification is impossible. Within the observable universe, our best theories leave 95% of its content unexplained. Our two most successful theories are mutually incompatible at their boundaries. The expansion rate of the universe is measured to be two different values by two equally reliable methods. Our most fundamental theory of matter makes its worst prediction in the history of science about the energy of the vacuum. The most intimate feature of human experience, the flow of time, is absent from the fundamental equations of physics. And the theory most likely to unify everything, string theory, currently makes no predictions that can distinguish it from its predecessors. This is the state of physics at the frontier. This is what the most advanced, most carefully tested, most rigorously verified science in human history has arrived at. Not a completed picture of reality, but a picture with enormous irreducible holes in it, holes that the picture's own internal logic has generated, and that the picture cannot fill from within itself. Let us dwell for a moment on something that rarely gets discussed directly, but that underlies everything. We have been exploring the relationship between human cognition and the nature of the universe. Because there is a possibility, a quiet, uncomfortable possibility, that some of what makes the universe seem so strange, so paradoxical, so resistant to comprehension, is not a feature of the universe itself, but a feature of the particular kind of minds that are doing the comprehending. Human cognition evolved to solve problems at a particular scale, the scale of objects a meter or so in size, moving at speeds much less than the speed of light, on timescales of seconds to years, under gravitational forces typical of a planet's surface. The neural architecture that processes sensory information and constructs models of the world was shaped by evolution to deal with predators, food sources, social dynamics, and environmental hazards, not with quantum superpositions or cosmological horizons or the topology of spacetime. It is entirely possible that some of the strangeness of quantum mechanics, the weirdness of superposition, the paradox of measurement, the non-locality of entanglement, is not deeply mysterious in some absolute sense, but appears mysterious because the human brain does not have the right kind of cognitive architecture to intuitively grasp it. A mind that had evolved in a quantum environment, that processed quantum information directly, that navigated a world of superpositions rather than definite objects, might find quantum mechanics perfectly natural and obvious in the way that three-dimensional spatial reasoning is natural and obvious to you. The mystery might be a cognitive artifact, not a feature of the universe, but a feature of the mismatch between the universe and the minds that are trying to understand it. This possibility, sometimes called cognitive closure by the philosopher Colin McGinn, suggests that there might be aspects of reality that are in principle incomprehensible to human minds, not because they are infinitely complex or because the relevant information is unavailable, but because human cognitive architecture is not the right kind of architecture to represent them. Just as a dog cannot grasp the concept of calculus, not because calculus is infinitely hard, but because the dog's neural architecture does not have the representational capacity for abstract symbolic mathematics, humans might be cognitively closed with respect to certain features of fundamental reality. We might be able to describe those features mathematically as we describe quantum mechanics mathematically, without truly understanding them, without having the kind of intuitive grasp that would allow us to say, yes, now I see why it is like this. The mathematics of quantum mechanics and general relativity works. We can use it to make predictions and build technology. But when we ask, what does it mean? When we ask for an intuitive, visualizable picture of what is actually happening, we find ourselves unable to provide a satisfying answer. This might be cognitive closure at work. The equations describe something real. The thing they describe is not something a human brain can intuitively model. And the theories we develop to interpret the equations, the Copenhagen interpretation, many worlds, relational quantum mechanics, and so on, are all attempts to find a story that a human brain can tell about what the equations say, rather than genuinely deeper insights into the underlying reality. They are translations into the language of human cognition of something that may not be fully translatable. If this is right, it has a profound implication for the future of physics. The next revolution, the theory that unifies quantum mechanics and general relativity, that explains dark matter and dark energy and the cosmological constant, might be a theory that we can formulate mathematically, that we can use to make predictions and build technology and advance science, but that we cannot truly understand in the way we understand Newtonian mechanics, with its simple visualizable concepts of force and mass and acceleration. It might be a theory whose conceptual foundations are accessible only through abstract mathematics, through tools of representation that go beyond what the human mind can intuitively grasp. Science would still work, predictions would still match observations, technology would still advance. But the question, what is it really like? The question of what the universe is like from the inside, what its fundamental nature actually is, might be permanently beyond the reach of human intuition, even if not beyond the reach of human calculation. There is something deeply disorienting about this possibility, not because it makes physics any less useful or any less intellectually exciting, but because it suggests that the goal of truly understanding the universe, of achieving a genuinely satisfying, intuitive, visceral comprehension of what reality is, might not be achievable. The universe might be knowable in a technical sense, tractable in a mathematical sense, exploitable in an engineering sense, and yet fundamentally opaque in the sense that matters most to the human mind. the sense of just getting it, the sense of seeing clearly. The universe might forever be something we can describe but never fully inhabit in thought. In 2016, LIGO detected gravitational waves for the first time. The detection was not just a confirmation of Einstein's prediction from a century earlier. It was the opening of an entirely new window on the universe, a new sense organ, in effect, through which humanity could begin to receive information about the cosmos in a medium completely different from light. For all of human history, everything we had learned about the universe had come through electromagnetic radiation, visible light, radio waves, X-rays, infrared, ultraviolet, the full spectrum. Now, for the first time, we were hearing the universe in gravitational waves, ripples in the fabric of space-time itself, carrying information about the most violent events in the cosmos, colliding black holes, merging neutron stars, possibly even the quantum fluctuations of the inflationary epoch. A new era of multi-messenger astronomy had begun. The importance of this cannot be overstated. Every time humanity has developed a new way of observing the universe, the first optical telescopes, then radio telescopes, then X-ray and gamma-ray satellites, it has discovered things that were completely unexpected. The universe has always been stranger than what the previous generation of instruments could reveal. Radio astronomy discovered pulsars, rapidly rotating neutron stars whose beams of radio waves sweep across the Earth like cosmic lighthouses, which were not predicted and whose discovery required the development of entirely new astrophysical theory. X-ray astronomy revealed the universe to be full of violent, high-energy processes, accretion disks around black holes, neutron star binaries, supernova remnants that were invisible to optical observation. Gamma-ray astronomy revealed gamma-ray bursts, the most energetic explosions in the universe, releasing in seconds as much energy as the sun will radiate in its entire 10 billion-year lifetime. With gravitational wave astronomy, we are now in the early stages of exploring a new territory. The LIGO and Virgo collaborations have cataloged dozens of gravitational wave events, binary black hole, mergers, neutron star mergers, and possibly the merger of a black hole with a neutron star. These observations have already revealed surprises. The masses of the merging black holes span a much wider range than stellar evolution theory predicted. There are black holes in mass ranges where they should not be able to form by standard mechanisms. The neutron star merger detected in 2017, GW-170-817, was observed simultaneously in gravitational waves and electromagnetic light, providing a new way to measure the Hubble constant. That measurement, you might already be guessing, gave a value somewhere between the CMB measurement and the distance ladder measurement, potentially consistent with both, but not yet precise enough to resolve the tension definitively. The next generation of gravitational wave detectors, the Einstein telescope in Europe, the Cosmic Explorer in the United States, and the space-based LISA observatory, will be sensitive enough to detect gravitational waves from much earlier in the universe's history, potentially from the epoch of inflation itself. If inflation produced gravitational waves, and most inflationary models predict that it did, then LISA and its successors might detect them directly, providing a window into the universe's very first moments that is otherwise completely inaccessible. The universe's birth might be directly observable, and what we find might confirm our current models, modify them, or, in the pattern that has characterized every previous expansion of observational capability, reveal something completely unexpected. There is also the matter of neutrino astronomy. Neutrinos are particles so weakly interacting that they can pass through the entire Earth as if it were not there. A cubic centimeter of matter contains about 65 billion solar neutrinos passing through it every second, and you feel nothing. But this ghostly imperviousness to ordinary matter also makes neutrinos extraordinarily difficult to detect. Large underground detectors, tanks of water or ice instrumented with thousands of photomultiplier tubes, can catch the occasional neutrino interaction, one in billions of passing neutrinos. The Ice Cube Neutrino Observatory at the South Pole, built into a cubic kilometer of Antarctic ice, has detected high-energy neutrinos from outside the solar system, opening another new observational window. And neutrino experiments have already produced one of the few confirmed empirical departures from the original Standard Model, the discovery that neutrinos have mass however tiny, which the original Standard Model predicted they could not. Neutrino masses are small, at least 1,000,000 times smaller than the electron mass, but they are not zero. This seemingly minor fact has large implications. It means the Standard Model is definitively incomplete. It means there is physics beyond the Standard Model that generates neutrino masses through a mechanism not included in the original framework. The two most popular mechanisms, the seesaw mechanism and the Majorana neutrino scenario, both involve new physics at very high energy scales, potentially as high as the grand unification scale. Neutrino mass is a crack in the Standard Model's completeness, small in its immediate practical consequences but significant as a signal that the universe contains physics we have not yet characterized. And then there is what cosmologists call the matter-antimatter asymmetry. The laws of physics as we understand them treat matter and antimatter almost identically. If you ran the laws of the Standard Model on a universe that replaced every particle with its antiparticle, turned every electron into a positron, every quark into an antiquark, the resulting antiparticle universe would evolve in essentially the same way as the particle universe, with only tiny differences associated with the weak forces charge parity violation. At the Big Bang, the laws of physics should have produced matter and antimatter in equal quantities. When matter meets antimatter, they annihilate in a burst of pure energy. A universe born with equal amounts of matter and antimatter should have ended up as a universe of pure radiation, with no residual matter at all. No stars, no galaxies, no planets, no chemistry, no life, no observers. Pure light, expanding into emptiness. And yet here you are, made of matter, sitting on a planet made of matter, orbiting a star made of matter, in a galaxy made of matter. The universe is overwhelmingly composed of matter, with essentially no primordial antimatter. For every billion pairs of matter and antimatter particles that were produced in the early universe and subsequently annihilated, there was one extra matter particle left over. That tiny asymmetry, 1 part in a billion, is the matter from which everything you have ever seen or touched or experienced is made. The protons in your body, the carbon in your DNA, the iron in your blood, all of it is the residue of a 1 in a billion excess of matter over antimatter in the first fractions of a second of cosmic time. And we do not know why that excess existed. The Standard Model's charge parity violation is far too small to generate the observed matter-antimatter asymmetry. There must be additional sources of asymmetry beyond the Standard Model, unknown physics that tipped the cosmic balance, however slightly, toward matter. Without that unknown physics, you would not exist. Stars would not exist. The universe would be dark and empty. And we have no confirmed theory of what that physics is. There is a question that has been lurking beneath everything we have discussed, surfacing occasionally in the language we have used but never stated directly. Now is the time to state it. The question is, why is the universe comprehensible at all? Why do the laws of physics take the form of elegant mathematical equations rather than some incomprehensible tangle? Why is the universe governed by symmetry principles? Conservation of energy, conservation of momentum, conservation of charge, that are deep and universal and can be expressed with beautiful mathematical precision? Why does mathematics, the product of pure human reasoning with no necessary connection to physical reality, describe the physical world so accurately that physicists can use it to predict the existence of particles before they are discovered, to calculate the behavior of atoms to 11 decimal places of precision, to describe the geometry of space-time across the entire observable universe? The physicist and Nobel laureate Eugene Wigner called this the unreasonable effectiveness of mathematics in the natural sciences. He had no explanation for it. It remains in a deep sense unexplained. Why should a universe that was not designed by human minds to be comprehensible to human minds happen to be governed by principles that human minds can discover and articulate with extraordinary precision? One answer, the Tegmark answer, is that the universe is a mathematical structure, and so of course it is describable by mathematics. Another answer is evolutionary. Human minds evolved in a universe governed by these laws, and so they developed the kind of cognitive capacities needed to detect patterns, to find regularities, to do the kind of abstract reasoning that ultimately, after a long journey, leads to physics. A third answer is that we have not explained the universe. We have only succeeded in finding mathematical descriptions that work within certain domains, and the success of those descriptions does not mean we understand why the universe has those particular laws rather than others. But there is a fourth answer, or rather a fourth non-answer, that is perhaps the most honest. We do not know. We do not know why mathematics describes the physical world. We do not know why the universe has the laws it has. We do not know why anything exists rather than nothing. The most fundamental question that can be asked, older than physics, older than science, older than civilization. Why is there something rather than nothing? Every physical theory assumes the existence of some substrate, space-time, quantum fields, a wave function of the universe, from which everything else is derived. But the existence of that substrate is taken as a given, not derived from anything more fundamental. Physics can tell you how the universe evolves from a given initial state. It cannot tell you why there is an initial state rather than nothing. The most fundamental fact of all, the bare existence of anything, lies outside the explanatory reach of physics, perhaps permanently. The philosopher Gottfried Leibniz asked this question in 1714, and 300 years of physics have not answered it. If anything, they have sharpened the edges of the mystery. Because now we know enough about the universe to know that its existence is not a simple, uncomplicated fact. The universe has specific laws, specific constants, a specific initial condition of extraordinarily low entropy, a specific slight preponderance of matter over antimatter, a specific value of the cosmological constant that is small enough to allow structure, but large enough to be measurable. All of these specificities require explanation. A universe with different specificities would be a different universe, possibly one that could not contain observers. The existence of this particular universe with all of its particular features is not a necessity. It is a contingency, and a contingency cries out for explanation. Some people find the anthropic argument satisfying. We are here, therefore the universe is the kind that allows us to be here, and no further explanation is needed or possible. Other people find this deeply unsatisfying, because it explains our existence by presupposing a vast ensemble of other existences that we have no direct evidence for, and it explains the specific features of the universe by a selection effect that requires the prior existence of a multiverse, which itself requires explanation. Why should a multiverse exist rather than nothing? Why should any mathematical structure exist rather than nothing? Why should existence itself be a feature of mathematical structures rather than a brute, unexplained fact? Every proposed answer pushes the why back one more level without eliminating it. The question of why there is something rather than nothing is, at present, an absolutely open question, with no answer that does not simply relocate the mystery rather than resolve it. We have come a long way from the beginning of this journey. We started with the promise, or warning, that something is wrong with the universe. We have walked through the evidence, the Hubble tension, dark matter and dark energy, the cosmological constant problem, quantum non-locality, the measurement problem, the incompatibility of general relativity, and quantum mechanics, the black hole information paradox, the arrow of time, the fine-tuning of constants, the failure to find supersymmetry, the matter-antimatter asymmetry. We have followed the implications into speculation, simulation theory, the mathematical universe hypothesis, relational reality, cognitive closure, the limits of what science can know. We have arrived at the deepest and most uncomfortable place, the recognition that the universe is not only strange, but strange in ways that resist resolution, in ways that our best intellectual tools may be constitutionally unable to penetrate. And yet there is something that needs to be said here, something that sits alongside all of the unresolved mystery, without diminishing it, but without being crushed by it either. The strangeness of the universe is not a failure of science. It is the product of science's success. Every anomaly we have discussed was discovered through careful, rigorous, honest scientific work. The Hubble tension would not exist as a named and studied problem if astronomers had not developed the capability to measure the expansion rate of the universe to 1% precision using two completely independent methods. The quantum measurement problem would not be a problem if physicists had not developed quantum mechanics to the extraordinary precision that makes its internal conceptual tensions visible. The cosmological constant problem would not be a problem if quantum field theory were not so extraordinarily successful at predicting everything else. The anomalies are the shadows cast by the light of knowledge. They exist because the light is bright enough to reveal them. A less advanced science would not have found them. This is the paradox of deep inquiry. The more accurately you describe the world, the more clearly you see the things your description cannot account for. Every improvement in measurement resolves some old mysteries and creates new ones. Every theoretical advance in precision reveals new anomalies that the theory did not predict. Science does not converge to a final picture that eliminates all mystery. It converges to a richer and more complex picture in which old mysteries are dissolved and new, deeper mysteries emerge. The frontier of knowledge is not moving toward a wall, toward a limit beyond which all questions have been answered, but outward into an ever-expanding territory of new questions, new anomalies, new strangeness. And this should not horrify you. It should, on reflection, be a source of something that is difficult to name precisely, a mixture of humility and exhilaration, of smallness and wonder. You exist in a universe that is older than the human species by a factor of more than 3 million, that is larger than your world by a factor of many billions of light years, that is composed mostly of things you cannot see or directly detect, that follows laws you have barely begun to comprehend, that contains within it structures and phenomena and scales of organization that have no precedent in anything that evolution equipped your brain to understand. And yet here you are, understanding something. Not everything, not even close to everything, but something real, something precise, something true about the physical universe in which you exist. The fact that you can hold in your mind the shape of the CMB power spectrum, or the mathematics of a geodesic in curved space-time, or the interference pattern of a single electron passing through two slits, the fact that the universe has produced minds that can even partially comprehend the universe, is itself one of the most astonishing facts of all, and one that no current theory fully explains. The physicist Lee Smolin has written that the most important question in physics is not any particular technical puzzle, but a deeper methodological one. What kind of universe is the kind that physics can work in? For physics to be possible at all, for the scientific method to be a viable way of learning about reality, the universe must have certain features. It must have reproducible phenomena. It must have laws that are consistent across space and time. It must have a structure that is at least partially accessible to the kind of abstract symbolic reasoning that human minds can do. The fact that our universe has these features is not obvious. It is extraordinary, and it is something that any complete theory of the universe will need to explain. Not just what are the laws, but why does this universe have the kind of laws that allow its inhabitants to discover the laws? This is not a question that any current theory answers. It is not a question that current science even has the tools to address. It is perhaps the kind of question whose answer lies on the other side of the next scientific revolution, the one that resolves the incompatibility of quantum mechanics and general relativity, that explains dark matter and dark energy, that addresses the cosmological constant problem and the matter-antimatter asymmetry and the Hubble tension. The question may be not just, what is the universe made of, but why is the universe the kind of thing that can be understood? And the answer to that question, if it ever comes, will almost certainly be something that no human mind alive today is prepared to imagine. There is a specific moment in the history of science that deserves to be mentioned here, because it foreshadows something important about the current moment. In the late 19th century, physics appeared to be nearly complete. Maxwell's equations described electromagnetism with breathtaking comprehensiveness. Newtonian mechanics described the motion of all objects from falling apples to planetary orbits. Thermodynamics described the behavior of heat and energy. The foundations seemed solid. There were a few small clouds on the horizon, a tiny discrepancy in the orbit of Mercury that Newton's theory could not quite account for, an inconsistency in how Maxwell's equations behaved under Galilean transformations, the ultraviolet catastrophe in the theory of black body radiation, small clouds, minor irritants, the kind of thing a few tweaks to the theory would surely resolve. Those small clouds turned into thunderstorms that demolished the entire edifice. The orbit of Mercury was explained by Einstein's general relativity, which in doing so replaced Newton's absolute space and time with curved spacetime. The inconsistency in Maxwell's equations led to special relativity, which replaced Galilean transformations with Lorentz transformations, and revealed that the speed of light is the same for all observers, regardless of their motion. The ultraviolet catastrophe was resolved by Planck's quantum hypothesis, which led to quantum mechanics, which replaced the deterministic, continuous universe of classical physics with a probabilistic, quantized reality. Within 30 years, the entire framework of 19th century physics had been replaced by theories so different in their conceptual foundations that scientists of the 1870s would barely have recognized them. The small clouds had been harbingers of a revolution. The anomalies we have been discussing are not small clouds. The Hubble tension is a 5 sigma discrepancy between two of the most precisely executed measurements in observational astronomy. The cosmological constant problem is a theoretical prediction that is off by 120 orders of magnitude. A discrepancy so large it does not have a precedent in the history of science. The failure to detect dark matter directly, despite decades of sensitive experiments and overwhelming indirect evidence for its existence, suggests either that we do not understand the particle physics of the dark sector, or that we do not understand gravity in the low acceleration regime. The black hole information paradox pits two of the most successful physical theories against each other in a direct, unresolvable contradiction. These are not small clouds. They are enormous, persistent, robust signals that something fundamental is missing. If history is any guide, the resolution of these anomalies will require not just new data or new calculations, but a genuinely new way of thinking about the universe, new concepts, new frameworks, new foundations. The revolution that is needed may be as profound as the one from Newtonian to Einsteinian mechanics, or as the one from classical to quantum physics. It may require the abandonment of concepts that currently seem irreducibly fundamental: space, time, causality, the distinction between observer and observed, in favor of new concepts that do not yet have names. And it may require an openness to strangeness, a willingness to follow the mathematics wherever it leads, even if where it leads is somewhere that human intuition cannot follow and human language cannot adequately describe. That willingness, the willingness to live with deep uncertainty, to hold open questions without forcing them to premature closure, to follow the evidence even when it leads toward conclusions that are uncomfortable, counterintuitive, or seemingly impossible, is not just a scientific virtue. It is perhaps the most important intellectual virtue of all. It is the disposition that made the quantum revolution possible, that allowed physicists to accept that reality at the smallest scales is irreducibly probabilistic, that matter has wave-like properties, that the act of measurement influences what is measured, that particles can be instantaneously correlated across arbitrary distances. None of those things should have been true. They were not what anyone expected. They violated the deepest classical intuitions about how reality should work. But the experiments demanded them, and science followed the experiments. The universe dictated the terms. The scientists listened. The same willingness is needed now. The experiments are speaking, again. The observations are insisting on something. The universe is, once more, refusing to fit the categories we have prepared for it. And the right response is not to dismiss the anomalies, not to insist that they must have conventional explanations within the current framework, not to wait for the discomfort to resolve itself. The right response is to listen carefully, to take the strangeness seriously, to follow it wherever it leads, with the same combination of rigor and imagination and radical openness that has always characterized science at its best and most revolutionary. Let us now sit with something that has been implicit throughout everything we have discussed, but has not been stated as clearly as it deserves to be. The universe is not just strange in its specific anomalies, in its dark matter and dark energy and Hubble tension. It is strange in its general structure. It is strange in the way it is put together, in the relationships between its scales, in the way physics changes character as you move from one scale to another, in the way the laws that govern the very small are completely different in their language and their ontology from the laws that govern the very large. Physicists sometimes talk about the landscape of scales, the enormous range of size, energy, and timescales that the universe contains, and the way different physics applies at different scales. At the scale of everyday objects, Newtonian mechanics is perfectly adequate. Add high speeds, and you need special relativity. Add strong gravity, and you need general relativity. Add small sizes, and you need quantum mechanics. Add high energies to small sizes, and you need quantum field theory. Add extreme gravity to small sizes, and you need quantum gravity, which we do not yet have. These different theories are not just approximations to a single underlying framework. They speak different mathematical languages, use different conceptual categories, describe reality in fundamentally different terms. The universe seems to have multiple, starkly different faces, each visible only at a particular scale, each disappearing when you move to a different scale, like aspects of an impossible figure that can only be seen from a particular angle. This scale dependence of physics is one of the deepest puzzles in the discipline. Why should the universe be this way? Why should the laws of physics at the Planck scale be so radically different from the laws at the macroscopic scale? Why should quantum mechanics and general relativity, both of which are in their respective domains extraordinarily successful, be so deeply, structurally incompatible at their boundaries? A fully unified theory of physics would presumably have a single set of laws that looked like quantum mechanics at small scales and like general relativity at large scales, in the way that Newtonian mechanics looks like special relativity at low speeds. But despite decades of effort, no one has written down such a theory in a form that makes specific, testable predictions about our universe. The unification remains out of reach, and here is something you should hold alongside everything else. The laws of physics, as we have them, describe what happens. They describe how the universe evolves from one state to another. They encode the regularities and symmetries that govern physical processes, but they do not explain why any of this is the way it is. They are descriptions, not explanations. Even the most fundamental principles of physics, the principle of least action, the gauge symmetries of the Standard Model, the equivalence principle of general relativity, are empirical discoveries about the structure of the universe, not logical derivations from first principles. They are the rules the universe happens to follow, not rules that it had to follow. And the question of why the universe follows these particular rules rather than some other set is a question that physics, and by its own methodology, cannot answer. Physics can only answer questions of the form, given that the universe follows these rules, what happens? It cannot answer why these rules, because answering that question would require a vantage point outside the universe, a perspective from which the universe's rules can be seen as contingent choices among a larger space of possibilities. Acquiring such a vantage point is not just technologically impossible. It may be conceptually impossible. The universe is the totality of what exists. There is, by definition, nothing outside it from which it can be observed as a whole, and its rules seen as contingent. Any explanation of the universe's rules must be made from within the universe, using the universe's own rules. which introduces a circularity that may be irreducible, unless, and this is where the speculation becomes necessary, because the alternatives are worse. The universe is one of many, embedded in a larger, mathematical landscape, and the rules it follows are contingent features of its particular region of that landscape. This is the multiverse argument again, in its most general form. The rules of the universe are what they are, because this particular region of the larger reality has these particular rules, and we are here because these rules allow our existence. But this argument, as we noted, either resolves the mystery by eliminating it, by saying there is no deep reason, only selection, or pushes it back to the question of what determines the larger landscape and what rules that landscape follows. The regress does not terminate. Every explanation requires a deeper explanation. The universe refuses to yield a bedrock from which everything else can be derived. This infinite regress of explanations is not unique to physics. It is a feature of every attempt to understand anything deeply. The philosopher's classic formulation is, if you explain the universe by reference to God, what explains God? If you explain God by reference to necessary existence, why should necessary existence be possible? If the laws of physics are mathematical truths, why should mathematical truths have physical instantiation? If the universe is a simulation, what are the rules of the simulator's universe and why do they have those rules? Every proposed bedrock dissolves under sufficient pressure into something that requires its own foundation. This is not a pathology of human thought. It may be a feature of the structure of explanation itself, a sign that reality does not have a foundation in the sense we are looking for, that the universe is not a structure resting on a base, but something more like a web, with no single node that grounds all the others, each part dependent on other parts in a complex, tangled pattern of mutual support without any ultimate anchor. Here is a fact that is worth sitting with as you approach the end of this exploration. Right now, at this moment, there are people in laboratories and observatories all over the world who are looking at data that does not fit the models. There are theorists staring at equations that will not close. There are graduate students in the middle of the night, surrounded by the glow of computer screens, watching simulations produce results that their supervisors told them should not happen. There are senior scientists at the apex of their careers who have spent 40 years building a theoretical structure and are quietly, privately beginning to wonder whether the foundation is sound. Science at the frontier is not a triumphant march forward. It is a sustained encounter with the limits of knowledge, a daily confrontation